Why are we here? What's the quick answer to that? There's a theory called eternal inflation, which is now being taught in universities. It says that we might live in just one universe in an infinite collection of other universes called a multiverse, in which every possible combination of the laws of nature occurs somewhere in its own separate universe. So everything that can happen happens. It is then inevitable that our universe exists as well. Why are we here? Because we have to be. That because we have to be answer sounds stark at first, almost dismissive, but it's really a statement about selection. If there is a process that produces many, perhaps infinitely many cosmic regions with different physical conditions, then observers will naturally find themselves in one of the rare places where the conditions allow observers. It's not destiny in the mystical sense, it's bookkeeping. To see why that idea has any force at all, we have to back up and look at the chain of reasoning that led physicists to eternal inflation, and by extension to a multiverse in which selection affects matter. Inflation began life not as a speculation about other universes, but as a practical fix to puzzles about this one. When we map the afterglow of the Big Bang, the cosmic microwave background, we see that the temperature is almost the same in regions of the sky that could never have communicated with each other if the universe had always been expanding a leisurely, steady rate. That uniformity is surprising. We also see that space is very nearly flat on large scales, as if geometric curvature were dialed down close to zero. And we don't see ancient relics predicted by some high-energy theories such as magnetic monopoles. Inflation solves these problems in one elegant stroke by positing that very early on the universe underwent an episode of extremely rapid, accelerated expansion. That burst stretches any initial curvature towards flatness, dilutes unwanted relics to near non-existence, and allows regions that were once in contact equilibrating their temperatures to be flung far apart later. It also gives us a way to seed the tiny ripples that would grow into galaxies. Quantum fluctuations of the field, driving inflation, get stretched to cosmic size and frozen in as faint density variations. So far, so compelling. Now, why eternal? Because when you combine quantum physics with that inflating field, you find that inflation doesn't end everywhere at once. Think of the inflating universe as a field perched on a plateau of potential energy. In some places, the field can roll down and convert its energy into hot matter and radiation, the beginning of a Big Bang phase like ours. But quantum jitters can push other patches of the field back up the plateau or keep them hovering there. Those patches continue to expand faster than the regions where inflation has ended. The result is a kind of self-reproducing fractal-like structure, a background that keeps inflating, studded with bubbles or pocket universes where inflation has stopped and normal cosmic evolution has begun. Each bubble is to its inhabitants an entire universe. If the underlying physics allows different low-energy outcomes, different values of the constants of nature, different particle masses, different amounts of dark energy, then different bubbles can realize different settings of the cosmic dials. In that setting, the anthropic argument becomes sharp. Most bubbles, if the range of possibilities is broad, will be sterile. The constants might yield only black holes, and radiation or inflation might end with such violence that complex chemistry never gets a foothold. A few bubbles will find themselves with just the right balance, stars that live long enough to forge carbon and oxygen planets with liquid water, and a background expansion rate that lets galaxies assemble before everything is dragged apart. If there are many bubbles, and at least some of them allow life, then it's unsurprising indeed, inevitable, that conscious beings will arise in one of those and ask, why this? The answer in that framework is because only these rare settings support beings who can ask. That's a powerful idea, but we should be honest about its status. Inflation as a general mechanism is well motivated and consistent with what we see. Some of its predictions, the near flatness of space, the spectrum of primordial fluctuations, match measurements. Eternal inflation is not an extra hypothesis bolted on. It tends to be what inflation does when quantum effects are included. But it's not the only conceivable early universe story, and it drifts toward territory where direct tests are hard. We cannot step across to another bubble and read off its constants. We look for indirect signatures, perhaps a collision between our bubble and another could have left a circular bruise in the microwave background. Perhaps primordial gravitational waves of a certain strength would point toward energy scales where eternal behavior is likely. So far we have constraints, not confirmations. That doesn't make the idea unscientific, but it does mean we should carry it with humility. Even within the multiverse picture, there are deep puzzles. If there are infinitely many bubbles and infinitely many ways for events to unfold, how do you define probabilities? This is the measure problem. Without a careful prescription for counting, you can get nonsense answers. You also have to worry about Boltzmann brains, hypothetical observers that fluctuate into being out of thermal noise in the far future, more often than ordinary observers like us formed by evolution, if the multiverse persists eternally in some states. Good theories should avoid predicting that most observers are disembodied brains with fake memories. Physicists work on versions of the measure that tame these pathologies and on models where the late-time behavior doesn't produce such absurdities. This is not philosophy for its own sake. It's an attempt to ensure that because we have to be isn't just a clever tautology, but a consistent statistical statement. If you prefer not to appeal to selection in a multiverse, there are other ways people try to answer why these laws. Some hunt for a deeper unification in which the constants we now measure are not freely adjustable, but determined by symmetry, or by the dynamics of a unique quantum state of the universe. Proposals such as the no-boundary idea in quantum cosmology imagine the universe as a finite self-contained whole described by a single wave function. In other directions, cyclic and bouncing models aim to replace the beginning with an eternal sequence of eons, or with a universe that contracts and re-expands, potentially washing away memory of previous cycles. Each of these approaches has successes and open problems. None has yet the crisp explanatory power and observational reach that inflation achieved for the horizon and flatness puzzles. The frontier is still genuinely open. When we ask why are we here, we usually mean more than why are there galaxies. We also mean why did the universe arrange the long chain of prerequisites for life? Here too, physics has things to say that are both modest and profound. You need time billions of years for generations of stars to live and die, enriching the cosmos with elements heavier than helium. You need planets, which likely means disks of gas and dust around newborn stars cooling and clumping, influenced by the details of chemistry and by the dance of gravity. You need stable energy gradients, sunlight bathing a planet or heat from the interior, so that complex molecules can form and sustain far from equilibrium structures. All of that depends on those dial settings, the strengths of fundamental forces, particle masses, the amount of dark matter and dark energy. Tweak some values too far, and you lose long-lived stars. Shift others, and you never get chemistry richer than hydrogen. Change the cosmic expansion too drastically, and galaxies don't aggregate. In that light, our presence does look like a narrow intersection of many requirements. There's also a why now question woven in. We appear to live at a cosmic moment a little over 13 billion years after the hot beginning, when star formation has already peaked, but galaxies are still abundant and luminous. It also happens to be a time when the density of dark energy is comparable to the density of matter, so the expansion has begun to accelerate, but the night sky is still full of neighboring galaxies. Some researchers have suggested that this too is a selection effect. Observers are more likely to measure the universe during epochs, when there are many bright galaxies to measure and when heavy elements have built up to make rocky planets, and biochemistry common. If there is a multiverse with a distribution of dark energy values, arguments first made in the late 20th century show that universes with much larger dark energy would expand so quickly that structure never forms. Of course, we do not see ourselves there. Notice what this sort of answer does and does not do. It does not whisper purpose into the equations. Physics, at least as we practice it, is not in the business of assigning goals to the cosmos. It tells us about mechanisms and tendencies, constraints and outcomes. The because we have to be line is not a claim that you or I as individuals were meant to exist. It's a claim that in a large enough ensemble of possibilities, regions consistent with life will be inhabited, and inhabitants will ask these questions. It moves why from intention to necessity. For many people that sounds unsatisfying, and it's worth acknowledging why. Human why questions usually have agency in them. Why is the kettle boiling? Because I turned it on to make tea. Cosmological why questions strip away the agent and replace it with dynamics. Why is the universe roughly flat? Because a period of inflation stretched it. Why does the electron have this mass? Perhaps because of symmetry breaking in a field it couples to, or because only in universes with close to this mass can chemistry flourish and therefore observers arise. Those are very different flavors of why. One is teleological, the other is structural. If you keep that distinction in mind, the scientific answers become clearer and more honest. Where does that leave meaning oddly in a space that is both smaller and richer? Smaller because the universe does not confer roles upon us from outside. Richer because the same laws that permit galaxies and life also allow conscious beings to make meaning. The hydrogen in your body was minted in a star. The carbon backbone of your cells was forged in red giants and scattered by supernovae. The iron in your blood began life in the hearts of the most massive stars, crushed and hurled into space in titanic deaths. The laws that enable that alchemy are the same laws that govern the expansion of space and the whispers of quantum fields at the dawn of time. In that sense, your existence is not an accident in the pejorative sense. It is a lawful unfolding of possibilities that the universe affords. Whether there are countless other universes or only this one, the story here is already extraordinary. It is also ongoing. We are still searching for traces of inflation in the polarization of the cosmic microwave background. We are measuring the distribution of galaxies to ever greater precision, mapping how structure grew under gravity and testing models of dark matter and dark energy. We are probing high-energy physics with colliders and astrophysical observatories looking for clues to unification that might fix the so-called constants. We are exploring exoplanets by the thousands, testing how common the conditions for habitability are. Every one of these investigations tightens or loosens the web of explanations that bear on that question, why are we here? So the quick answer, because we have to be, is a doorway, not a wall. Walk through it, and you find a landscape where inflation links the largest scales to quantum fluctuations, where selection effects make sense of apparent fine-tunings, where open problems keep the field honest, and where the absence of cosmic purpose does not diminish the wonder of being part of the universe that can know itself. If we do live in a multiverse, then our patch is one island, among many in a vast sea of possibility. If we don't, then the unique island we inhabit is still a place where atoms become life, and life becomes mind. In either case, our presence is a testament to the richness of the laws we've discovered and the depth of the questions we can ask. And that, I think, is the right way to hear the answer. Not as fatalism, but as an invitation to understand the mechanisms that make existence possible, to test them with the best tools we can build, and to let that understanding sharpen our sense of value and responsibility here in the one universe we can see under the quiet light of stars that made us. If the multiverse is a doorway, then just beyond it lies another room full of questions that feel even more intimate. Not only why these laws, but why this story? This unfolding from simplicity to complexity, from a smooth fireball to stars, planets, oceans and minds that can trace the arc back to the beginning. There is a thread that ties those together, and it runs through one of the most underappreciated facts about our reality. The universe began in a very special state of astonishingly low entropy. That sentence can sound technical, but it's really about the possibility of memory, of evolution, of time that feels like it's going somewhere. Entropy, in simple terms, is a measure of how many microscopic arrangements correspond to what you see macroscopically. A neat stack of papers on your desk has low entropy because there are relatively few ways to arrange the sheets and still call it neat. The same papers scattered by a gust fill the room with possibilities. That's higher entropy. Left to itself, a system tends to wander towards the states with the most possibilities, the messy ones, simply because there are vastly more of them. That gentle drift from order to disorder is what we call the arrow of time. Now, the early universe looked very uniform matter, and radiation smoothed out almost perfectly. By everyday intuition, uniform states feel disordered, but gravity flips the script. For a gas in a box without gravity, uniformity is high entropy. With gravity, uniformity is special and low entropy because gravity wants to clump. A slightly lumpy universe will over time amplify those lumps. Regions collapse into stars, galaxies, and eventually black holes, which are intriguingly among the highest entropy objects we know. So the hot, nearly smooth beginning is the neat stack of papers for the cosmos. It allowed the universe to run downhill for billions of years, turning gravitational potential into the structure we see, and creating the steady cascades of usable energy, sunlight warming a cool planet, hot interiors venting into cold space, that living systems exploit to build and maintain themselves. That low entropy beginning is as essential to our presence as the values of the constants. Without it, there would be no persistent arrow of time, no reliable cause and effect, no way for complex chemistry to climb by small steps from simple molecules to replicators to cells and beyond. You might ask sensibly why the universe started in that special state. We do not yet know. Some ideas appeal to deep principles, perhaps. The boundary conditions are fixed by a law as fundamental as the dynamical equations themselves. Others argue that inflation naturally smooths and flattens, turning a range of initial conditions into the kind of low gravitational entropy state we observe. There are bold suggestions that tie the low entropy past hypothesis to geometric features of spacetime or to a selection effect in a larger cosmological setting. At present, it is an open problem, one of the most beautiful, because it links the thermodynamic arrow to the existence of memory and meaning. If the arrow of time provides the slope, the constants of nature set the texture of the landscape down which the universe flows. Consider dark energy, the mysterious pressure that accelerates cosmic expansion. If its value were much larger and positive galaxies would be torn from one another before they could form, the primordial ripples seeded during inflation would never grow into stars. If it were large and negative, the universe would recollapse swiftly. We find ourselves in a cosmos where dark energy is small and positive, gently winning the tug of war only after galaxies have assembled. It is exactly the sort of value that selection arguments in a multiverse make plausible: too big and no observers, too negative and no time. Or consider the strength of the nuclear and electromagnetic forces that control stellar furnaces. Stars earn their long lives by balancing gravity's inward pull with the outward pressure from nuclear fusion. Nudge the forces and the balance changes. If the strong nuclear force were a bit weaker, the deuterium bottleneck in stellar cores might never break. If it were stronger, heavy elements could be burned through too quickly. The electron's mass, the neutron-proton mass difference, the charge of the electron, these small numbers set the rules of chemistry, determine the stability of atoms and molecules, and shape the palette from which biology paints. It is a delicate-looking arrangement. Whether the apparent delicacy is an illusion because a wide range of values would still work, or a genuine tightrope is something we continue to study. But the fact remains, the laws and constants we measure permit a universe with durable stars, rich chemistry, and long-lived islands of free energy. Those are the pillars on which life rests. Between those pillars, the universe is a grand non-equilibrium machine. It is not on the whole in thermodynamic balance. It is transitioning from the ordered gravitational initial state to a future of higher entropy. Along the way, it creates and sustains patterns that would be impossible in equilibrium, like whirlpools in a river, or convection cells in a heated fluid, only vastly more intricate. Life is one such pattern, a network of molecular reactions that uses free energy to maintain internal order while increasing entropy overall. The physicist Ilya Prigogine called such persistent energy throughput structures dissipative, which sounds unromantic, but captures the essence: we persist by burning gradients, temperature differences, chemical potentials against the universal trend. The cosmos provides the gradient, stars against the cold night, hydrothermal vents against the abyss, even the slow cooling of the universe itself. Whether there is life elsewhere depends not only on the prevalence of planets and water, but on the availability of suitable gradients and the pathways chemistry can take to harness them. On that front, we have learned something both humbling and exhilarating. Planets are, it seems, common. Solar systems are messy sculptors, and the disks of gas and dust around young stars readily coalesce into worlds. We have found thousands, with more arriving year by year, and their diversity is staggering hot. Jupiters grazing their stars, super-Earths and mini-Neptunes packed into tight orbits, temperate rocky planets in the habitable zones, where liquid water could exist. The details will continue to change as we refine measurements, but the broad message is secure. Our solar system is one arrangement among many. Chemistry is universal. Water is abundant. Carbon, nitrogen, oxygen, phosphorus, sulfur. The building blocks of biochemistry are forged in stars and strewn through space. The question of life's origin turns less and less on whether the ingredients exist, and more on how readily they self-organize into the first self-replicators. Here too, the arrow of time and the cosmic environment matter. On young planets, cycles of wet and dry, hot and cold, irradiated and shielded provide the rhythms that can drive prebiotic chemistry. Mineral surfaces can act as scaffolds. Ultraviolet light can both destroy and create. Networks of reactions can, under the right conditions, bootstrap themselves into structures that store information and catalyze their own persistence. We do not yet have a single agreed-upon pathway from geochemistry to biology, but we have promising laboratory hints and a growing theoretical framework that sees life not as a singular miracle, but as a possible, perhaps even probable, outcome given certain flows of energy and matter. That is a powerful shift. It moves the origin of life from the realm of special pleading to the realm of testable mechanism. When we look beyond origin to evolution, selection again enters the picture, but now Darwinian rather than anthropic. Given the opportunity to replicate imperfectly systems, explore possibility space, the environment filters, complexity accumulates where it helps. And because the planet is not isolated, because the sun shines and the planet cools, the supply of free energy maintains a stable, long-term context for that exploration. Over hundreds of millions of years, you get the staggering tapestry of life we see in the fossil record and in the living world, and eventually somewhere, eyes to see and minds to wonder. From the perspective of physics, this is not an accident in the sense of being uncaused or inexplicable. It is a particular contingent unfolding permitted by the general necessary frameworks of thermodynamics and dynamics. That distinction between the general and the particular is crucial if we want to be honest about why we are here. Physics gives the canvas and the rules. Evolution paints with the local colours. But there is another question lurking: if these conditions are not unique, where is everyone? This is the paradox Enrico Fermi famously posed in a lunchroom decades ago. In a galaxy with hundreds of billions of stars and billions of years of opportunity, why have we not seen unmistakable signs of other technological civilizations? Vast engineering projects, focused beams, clear beacons. There are many possible answers. Perhaps we are early. Perhaps life is common, but complex technological life rare. Perhaps civilizations are fragile, subject to filters, some self-inflicted, some environmental. Perhaps our search strategies are still naive. The cosmos is vast, and our instruments have only recently grown sensitive enough to even pose the question seriously. The paradox is a reminder that permitted is not the same as guaranteed. It keeps humility in the foreground as we look for biosignatures in exoplanet atmospheres and for technosignatures in the sky. Underneath all of this, the low entropy, past the constants, the emergence of complexity sits quantum theory, the engine of modern physics. It is quantum fluctuations that seed the structure of the universe in inflationary scenarios. It is quantum statistics that set the behavior of matter at high densities in stars and at low temperatures in interstellar space. It is quantum chemistry that builds the toolkit of life. And yet there are aspects of quantum mechanics that still provoke deep debate, especially when we ask cosmological questions. What exactly is a measurement in a universe that may be all there is with no outside observer? How does classical reality tables and chairs, stars and galaxies emerge from a wave function that in principle allows for many simultaneous alternatives? Decoherence theory explains how interactions with the environment suppress interference between alternatives and make classical behavior robust. But when the universe is the environment, the questions blur. Some interpretations extend quantum branching to the entire cosmos. Others seek a unique history. These are not mere philosophical flourishes. They feed back into how we think about initial conditions, about probability in an inflationary multiverse, and about what we mean when we say this happened. I find it helpful when the abstractions threaten to float away to return to one plain picture. A little over 13 billion years ago, our observable patch was hot, dense, and astonishingly smooth, with tiny, almost imperceptible ripples. Those ripples grew under gravity, forming a foam of dark matter halos that gathered ordinary gas. The gas cooled, spun, fragmented, and lit the first stars. Those stars forged heavy elements. Their deaths seeded the next generations. Disks around young stars deepened into planets. On at least one of those, chemistry found a foothold and climbed. Everything we care about is one branch on that tree. Change the early ripples and the tree looks different. Change the constants and the tree might never sprout. Change the entropy of the beginning and the tree is never planted. That is the sense in which the scientific answer to why are we here is about preconditions rather than purposes. It does not tell us what to do, it tells us what made doing anything possible. There is one more layer we should add because it completes the circle. The same laws that allowed us to exist also let us become knowers. The universe is intelligible, at least in part. Mathematics written on a blackboard in a lecture hall can capture the workings of stars light years away and the structure of space-time itself. That correspondence, the unreasonable effectiveness of mathematics, as Wigner put it, might itself be a selection effect of a different kind minds that can survive and build tools, are those that compress regularities into compact descriptions. They find the patterns because pattern recognition is their evolutionary strength. In that sense, the intelligibility of the world is not a gift from outside, but a match between the world's lawful regularities and our evolved capacity to notice them. Physics codifies those regularities efficiently. When we say because we have to be, we're also saying because this is a world where regularities endure long enough to be learned. So if we stitch the pieces together, a picture emerges. Inflation, or something like it, prepares a smooth, flat, causally connected stage and seeds gentle ripples. A low entropy start grants an arrow of time and a long downhill for structure to form. The constants of nature fall into ranges that yield durable stars and rich chemistry. Non-equilibrium flows carve out channels where complex structures can persist. On at least one world, chemistry discovers self-copying and bootstraps into evolution. Given time, eyes open, hands build, minds ask. None of these steps are guaranteed in every cosmos, perhaps not even in most, but in a vast space of possibilities, they are not vanishing miracles either. And if a multiverse exists, selection explains why we find ourselves in a rare but habitable neighborhood. If no multiverse exists, then we inhabit a singular universe whose laws nonetheless suffice. The rarity remains, the gratitude is the same. Where does this take us next? We should talk about tests, how ideas like inflation and selection, low entropy beginnings and quantum seeds leave traces we can look for in the sky and in the laboratory. The wonder is not diminished by testability, it is amplified by it, because every successful test turns speculation into knowledge, and every failure teaches us where to look again. Let's turn then to the evidence written on the oldest light in the universe, and the faint gravitational murmurs from its earliest moments, and ask what they reveal about the paths that led eventually to us. Evidence is our compass, and the sky is full of it. When we say inflation took a tiny, hot, almost featureless patch and stretched it into the vast observable universe, we're not simply telling a pretty story, we're pointing at fingerprints we can actually measure. The most famous of those is the cosmic microwave background, the afterglow released when the universe was a few 100,000 years old, cool enough for electrons to settle into atoms so that light could travel freely for the first time. Today that light arrives as a nearly uniform bath, a few degrees above absolute zero. But it isn't perfectly smooth. It's mottled at the level of 1 part in 100,000 tiny hot and cold spots scattered across the whole sky. Those blemishes are not noise. They are the fossilized imprints of sound waves, ringing through the young cosmos waves, seeded by quantum fluctuations and amplified by gravity. If you take that mottled sky and do something very down-to-earth, plot how much contrast there is as a function of angular scale, you get a series of peaks and troughs like a musical spectrum. The first peak tells you the size of the sound horizon, the distance those primordial pressure waves could have traveled before the afterglow was released. That acts as a standard ruler. The relative heights of the peaks tell you how much ordinary matter there was, how much dark matter, how tightly gravity and radiation were coupled, and how fast the universe was expanding at that time. The overall shape tells you about the initial ripples themselves, how close to scale invariant they were, whether they tilt slightly to favor large or small scales. Inflation makes very specific broad predictions here. Space should be very nearly flat. The initial spectrum of ripples should be close to but not exactly equal power on all scales, and those ripples should be almost perfectly Gaussian random in a very particular, simple way. Measurements of the afterglow sky have consistently landed right in that territory. Space is astonishingly flat on cosmic scales. The tilt is small and in the direction inflation likes, and the statistics are close to Gaussian, to within tight limits. There's more in that light than temperature. When light last scattered off electrons in the young universe, it became faintly polarized, and the pattern of polarization carries extra clues. You can decompose the polarization into two types: E modes, which look like whirls that can be made from a gradient, and B modes, which are the curl-like patterns you cannot get from a gradient alone. Ordinary density ripples, those that grow into galaxies, generate E modes quite readily, but not primordial B modes. Inflation, however, does something else. It also excites a background of gravitational waves, ripples in space-time itself. Those primordial gravitational waves would imprint a very specific B-mode pattern on the polarization of the afterglow. Detecting that pattern would be like hearing the faint hum of the universe's birth cry across billions of years. So far, we've mapped the E-modes exquisitely and seen that they line up with the story told by temperature. The B-modes are harder. The cosmos is messy. As afterglow light travels to us, it is gravitationally lensed, deflected by the intervening web of galaxies and dark matter, and that lensing converts some E into B, producing a foreground of B modes that must be carefully removed to reveal the primordial signal underneath, if it exists at a detectable level. We've become good at this delensing, but the primordial B mode, if present, is faint. The upshot is that we have stringent upper limits on the amplitude of inflation's gravitational waves, which already rule out a swath of the simplest, highest energy inflation models. New instruments are pushing further, Null results here are not disappointments, they are instructions telling us which versions of the early universe story can't be right. The afterglow is our oldest picture. The three-dimensional distribution of galaxies is our adolescent portrait. Gravity, working on those tiny initial ripples, built a cosmic web clusters at the knots, filaments in between, and vast empty voids. If you survey millions of galaxies and measure how they are spaced, you recover the same ruler we saw in the young universe, the imprint of those ancient sound waves now frozen into the positions of galaxies as baryon acoustic oscillations. It is extraordinary that a pressure wave in the hot plasma of the infant cosmos leaves a preferred separation scale that we can still detect in maps of galaxy positions billions of years later. That fossil ruler lets us measure the expansion history, how fast the universe has been growing at different epochs. Put that together with the afterglow and supernova observations, and you get a remarkably consistent picture. A cosmos dominated today by dark energy with an equation of state parameter very close to -1 behavior, like a cosmological constant, plus dark matter and ordinary matter in the proportions the afterglow implies. This triangulation is important for our question. If the value of dark energy is a selection effect in a multiverse, large values sterilize universes by preventing structure formation, then we should measure a small positive value, one that begins to bite only after galaxies have formed. That is exactly what we seem to see. But selection is not an explanation until you rule out dynamics. A true cosmological constant should be exactly constant. Alternatives, fields that slowly roll or interact, could evolve with time. So we test. We measure the expansion at many epochs, we watch the growth of structure, and we look for any deviation from the constant case. So far, within current precision, the data say constant. If better measurements continue to say the same, then the anthropic argument gains plausibility. If the data begin to drift, we will follow them and revise our stories. Inflation itself carries other testable details. One is non-Gaussianity, small departures from the simplest random statistics in the initial ripples. Many single-field slow-roll models predict these departures should be tiny, so tiny that we shouldn't expect to see them with current instruments. Other models predict larger signals. Surveys of the afterglow and the distribution of galaxies find that if non-Gaussianity is there, it is small. Again, that prunes the theoretical thicket. Another test comes from the overall curvature of space. Inflation tends to drive curvature to zero, but in some versions, especially those with fewer e-folds of expansion, a small residual curvature could remain. Observationally, curvature is constrained to be extremely close to flat. And then there are more speculative signatures. If our bubble of hot Big Bang collided with a neighbour early on, the bruise might appear as a circular feature in the afterglow map. Searchers have looked, nothing convincing so far. Absence of evidence is not evidence of absence, but it does tell you how rare or subtle such events must be. Gravitational waves provide a second complementary listening post on the early universe. The detectors we have now, laser interferometers on Earth, are exquisitely sensitive to the coalescence of black holes and neutron stars. Those events sing in the audio band, lasting fractions of a second to minutes. Inflation's waves, by contrast, would form a stochastic background spread across a huge range of frequencies, from the extremely low billions of years per oscillation up to frequencies beyond the reach of existing instruments. Different technologies explore different bands: pulsar timing arrays probe nanohertz, looking for correlations in the tick-tock of millisecond pulsars across the sky. Space-based interferometers will target millihertz. Future ground-based instruments push into the audio band with greater reach. There are already strong hints of a gravitational wave background at the lowest frequencies, likely from orbiting supermassive black hole binaries in merging galaxies. That's a triumph of a different kind of cosmology, the story of structure formation. The primordial contribution from inflation, if it exists, is expected to be weaker, but if detected in any band, it would give us a direct handle on the energy scale of the early universe and anchor the inflationary picture with a new kind of evidence. If you step sideways from dynamics to dial settings, there are tests for those as well. Are the so-called constants of nature truly constant? Atomic clocks on Earth can compare frequencies with absurd precision, constraining any present-day drift in the fine structure constant or the electron-proton mass ratio. Geologic records like a natural uranium reactor that ran in Gabon nearly 2 billion years ago let us test whether nuclear physics has changed over deep time. Astronomers look at absorption lines from distant clouds against background quasars to see whether the constants have shifted across billions of years and vast distances. So far, The safest thing to say is that any changes must be tiny. That consistency supports the idea that our local physics is stitched into the fabric of the whole observable patch. If we someday saw a clear spatial gradient in a constant, the door would swing open to more exotic ideas about variation across the larger cosmos. Then there is the thermodynamic arrow, the low entropy beginning we talked about, and the question of what would count as progress there. It is harder to test directly because it's a statement about boundary conditions rather than dynamical evolution, but it isn't beyond reach. One avenue is theoretical. Can a compelling, simple law pick out that kind of beginning in a natural way? Another is indirect. Does a more complete understanding of gravity's microstates, quantum gravity, in other words, clarify how to count gravitational entropy so that special at the beginning is properly defined? Black hole thermodynamics suggests that horizons carry entropy proportional to their area. If space-time geometry itself has microscopic degrees of freedom, perhaps the right measure of gravitational disorder is tied to the curvature in a way that explains why the early universe sat in a very low Weyl curvature state. These are conjectures with teeth because they connect to engines. We can test the evaporation of black holes in principle, the behavior of quantum fields in curved space-time, and the statistical underpinnings of geometry. Our place in this picture is not passive. The same methods that test cosmology also open the way to answering the question that most sharply confronts selection arguments. How common are worlds like ours, not just in the coarse sense of stars and planets, but in the precise sense of chemistry that runs away into biology? Here too, the approach is empirical. We observe atmospheres of exoplanets and look for gases far from chemical equilibrium, oxygen alongside methane, for example, because life is very good at maintaining disequilibria. We check for confounders. Some stars can split water molecules and leave oxygen behind without life. Some geologies can leak methane without biology. We build a roster of biosignature pairs and triplets that are hard to fake together. And we keep adding context: the planet's mass and size, its temperature and stellar environment, its likely geologic cycles. So far, we have made spectacular strides in measuring giant planets and hot, puffier worlds. Temperate, rocky planets are harder, but the path is clear. A single convincing biosignature would not answer why are we here in the deep sense, but it would answer, are we unusual, in a way that would reverberate through philosophy and science alike. And then there are technosignatures, signs not merely of life, but of technology. Narrowband radio signals remain a classic target because nature rarely makes them. Pulsed lasers are another possibility. Waste heat from large-scale energy use would glow in the infrared. We have found none that stand up to scrutiny. Some apparent oddities, stars dimming in strange ways, have natural explanations once the data improve. This again is not a disappointment, it's a calibration. It tells us what the night sky is like in a universe where mind and machine have not left conspicuous marks, at least not within our current reach. It encourages us to broaden the search with humility and patience. At every turn, the pattern is the same. The big ideas, eternal inflation selection, effects the arrow of time, are built on modest concrete observables. Map the oldest light and read its ripples. Count galaxies and measure their clustering. Listen for space-time's tremors. Weigh the expansion with standard candles and standard rulers. Time the ticks of pulsars. Compare the frequencies of the best clocks ever made. Watch the spectra of distant worlds for breaths out of equilibrium. None of these by themselves writes the final paragraph. Together they sketch a coherent story and mark the places where we do not yet understand the plot. And perhaps that's the most important point to carry. Because we have to be is not the end of curiosity, it's the beginning of a research program. If selection plays a role, we should see certain things and not others. A small, positive, dark energy density, near flat geometry, long-lived stars, chemistry's broad palette, an abundance of planets. We do see those. If eternal inflation is the engine, then at some level there should be traces of its gravitational waves, or at least an absence of features that contradict its simplest consequences. So far, the engine is consistent with the dashboard. If the low entropy beginning is essential, then any deeper theory of gravity and quantum mechanics must be compatible with an arrow of time that emerges naturally. Otherwise, it is not a theory of our world. That is a high bar, and it is good that it's high. Where do we go next? We tighten the screws. We look harder for primordial B modes and for departures from a perfectly constant dark energy. We map the cosmic web with greater fidelity, pushing into earlier times. We measure the masses of neutrinos by their gentle smoothing of structure. We attempt to delens the afterglow sky to its primordial clarity. We turn bigger mirrors and sharper spectrographs towards small dim worlds bathed in starlight. We allow ourselves to be surprised. Because if there's one reliable rule in the history of cosmology, it's this: the universe is not obliged to fit our first ideas, but it rewards careful questions with deeper coherence. And having followed the evidence from the oldest light to the newest worlds, a natural bridge appears. We've talked about conditions, we should talk about consequences. If the cosmos provides the right raw materials, gradients and time, how does lifeless chemistry become living metabolism? And how does that in turn become minds capable of physics? In other words, how do the laws that make us possible also make us curious? Let's turn to that bridge, the emergence of life and meaning from matter, and ask what physics can and cannot tell us about the first spark, the climb to complexity, and the strange, wonderful fact that the universe is knowable. If you want to see the bridge from matter to meaning, start with a planet that is not yet alive and ask what physics gives you for free. You have gradients, heat flowing from hot interiors to cold space, sunlight pouring across a vacuum to bathe a cool surface, chemical imbalances set up by rocks, water, and a restless atmosphere. You have cycles, day and night, tides, seasons wet and dry, freeze and thaw, and you have a periodic table whose elements forged in stars are promiscuous in the best possible way. Carbon forms long chains and rings, oxygen makes strong directional bonds. Nitrogen and phosphorus lend themselves to energy-rich linkages. These are not accidents in the storybook sense, they are lawful outcomes. Physics promises that if you supply energy and allow matter to explore configurations, some arrangements will persist longer than others. Some will help to generate copies of themselves. In a universe with an arrow of time, persistence, and copying become the currency of complexity. Prebiotic chemistry in that light is the art of discovering pathways from simple molecules to reaction networks that store information and harvest energy. There are many plausible venues. On the seafloor, alkaline hydrothermal vents build natural proton gradients as warm mineral-rich fluids bubble into cold ocean water. Those gradients are not abstract. They are batteries ready, made by geology. In shallow ponds and tidal flats, cycles of hydration and dehydration drive condensation reactions, stitching small molecules into longer polymers on mineral surfaces that act as scaffolds and catalysts. Ultraviolet light, destructive in high doses, can also be creative. It pumps energy into bonds and opens reaction channels that would otherwise remain closed. Each setting supplies the same two themes in different costumes: a steady flux of free energy and an environment that keeps selecting and templating useful structures. At some stage, information enters the picture, and with it a new kind of causation. A strand of RNA or something functionally similar can carry a sequence that both encodes a shape and in that shape catalyzes its own copying or the production of helpers. That duality is intoxicating hardware and software, entangled in a single molecule. It is easy to overstate what we know here. We do not have a single definitive path from geochemistry to the first replicator. But we have pieces that fit together promisingly. Clay minerals like montmorillonite can promote the assembly of nucleotides into short RNA-like chains. Lipids spontaneously form vesicles, little compartments that can grow, divide, and trap catalysts. Simple metabolic cycles can be driven by geochemical gradients, hinting that metabolism first and genes first stories may be two sides of a single coin braided together by compartments that keep useful reactions close and harmful ones out. Thermodynamics doesn't resist this story, underwrites it. A living system is not a violation of the second law. It is a highly efficient way of increasing entropy in the surroundings while maintaining internal order. You can think of life as a conduit that turns concentrated energy, sunlight, redox gradients, geothermal heat into diffuse waste heat and higher entropy with a byproduct of intricate structure. The secret everywhere you look in biology is coupling. Exergonic reactions, those that release energy, are chained to endergonic ones, those that require energy so that the unfavorable steps can proceed. Early life almost certainly used pre-existing gradients directly. Modern life does something universal. It builds and taps gradients across membranes. That is chemiosmosis, the insight once controversial and now central that cells pump protons across a barrier and let them flow back through a rotary enzyme ATP synthase to make the energetic coin of the realm. The rotary motor that spins in almost every cell on Earth is a nanoscopic turbine, a device so general that bacteria, plants and animals all use variations on the same theme. That universality is a clue that the first successful solutions to the energy problem were discovered very early and proved so effective that every lineage kept them. Information must be copied, and copying must be good enough to preserve what works but imperfect enough to explore. There is a balance to strike. Too much error and information cannot persist. Too little and adaptation stalls. In molecular evolution, that boundary is sometimes called an error threshold. Life learns to live near it with proofreading enzymes, repair pathways, and redundancy keeping mutations within a range where selection can operate. The nearly universal genetic code, the mapping from three-letter words in RNA to amino acids in proteins, looks like a frozen accident at first glance, but it also has error-minimizing properties. Single-letter mistakes often substitute chemically similar amino acids, softening the blow. Whether that code was selected for robustness, or whether robustness is a happy byproduct of how the code evolved, the effect is the same. It makes navigating the space of possible proteins less treacherous. From the first replicators to the last universal common ancestor is a journey hidden from direct view, but the shared features of life today let us infer a great deal. The ancestor was cellular with lipid membranes, proton gradients, ribosomes translating RNA into proteins, and a core metabolism that looks strikingly conserved. It probably lived in an environment where hydrogen, carbon dioxide and minerals were abundant, perhaps a vent, perhaps a terrestrial hot spring. It harvested energy by moving electrons down potential steps and used a remarkably small set of reactions to assemble the building blocks of life. The details will keep shifting as biochemistry and geology teach us more, but the contour is plain. Life did not begin with the complexity we know. It climbed a staircase whose rises were laid by the physics of gradients and information. Complexity, once it has a foothold, tends to ratchet. Cells aggregate into communities. Symbiosis flourishes. Genes that once floated freely become locked in long-term partnerships. One such partnership changed the world. A larger cell engulfed a smaller one and kept it as a power plant. The smaller cell became the mitochondrion. The larger became the ancestor of animals, plants, and fungi. That endosymbiotic leap gave eukaryotic cells an order of magnitude more energy per gene, opening the door to bigger genomes, elaborate internal scaffolding, and compartmentalized chemistry. Around the same deep time, photosynthesis began to split water, flooding the oceans, and later the atmosphere with oxygen. A poison at first, then a liberator of energy-rich metabolisms. The planet cooled and almost froze more than once. Ice retreated, ecosystems diversified. Somewhere in those long ages, multicellularity evolved several times, and with it the division of labor development bodies that could sense and move and learn. Nervous systems are what you get when information processing and movement become intimate. A neuron is a cell optimized to integrate many inputs over time and space, and to send a clear signal onward. Networks of neurons learn by altering the strength of their connections in response to activity and reward. That plasticity makes the brain a prediction machine. It builds models of the world, tests them against incoming signals, and updates them continuously. Those models are not separate from the physical structures that carry them. They are dynamic patterns in a biological organ, sculpted by evolution to exploit regularities in the environment. Language supercharges this process by allowing models to be shared and refined collectively. Writing and mathematics extend memory and inference outside the brain into marks and symbols that can persist for generations. Tools and instruments further extend our senses. The eye becomes a telescope, the ear a radio dish, the fingertip a scanning probe that feels atoms. When we ask how physical law gives rise to minds that do physics, the answer is not mystical, it is recursive. The universe supplies lawful, compressible patterns. Evolution favors organisms that can compress patterns into useful predictions. Culture accumulates those compressed descriptions, and science systematizes the accumulation with discipline, reproducibility, measurement, skepticism, and a willingness to discard beautiful ideas that fail. Mathematics sits at the heart of this because it is the language of compression. Equations are recipes that generate many facts from few assumptions. The law of gravitation is not a string of numbers. It is a compact statement that yields planetary orbits, falling apples and tides as corollaries. Whether mathematics is discovered or invented may be an unhelpful dichotomy. What matters is that certain mathematical structures map well onto the structure of the world, and that mapping lets us predict and explain. Seen this way, the emergence of meaning is not a ghost in the machine, it is a pattern of patterns, a feedback loop in which matter, energetically driven and shaped by selection, comes to model itself. You can locate purpose here without violating any law. Purpose in the biological sense is a shorthand for the stable outcomes of selection. Eyes are for seeing because organisms that saw survived. Hearts are for pumping because that is what conferred persistence. Human purposes blossom from that root into art, ethics, and science. They are not imposed by the cosmos. They are authored by agents the cosmos made possible. And yet they are not arbitrary. They remain tethered to the same reality that made them possible, because predictive success and practical flourishing require respect for how the world is. This perspective also reframes the Fermi question. If minds are pattern-recognizing, prediction-making machines built atop a long chain of thermodynamic and biochemical luck, how often does that chain close? The galaxy is vast and old. The preconditions for life seem generous, and yet the sky is quiet. Perhaps the quiet is temporary, an artifact of our recent arrival and our limited reach. Perhaps the widest bottlenecks lie not at origin, but at the transitions to intelligence, technology, and sustainable longevity. Minds can model their environment. They can also model themselves and misjudge. If meaning is local and authored, then stewardship, learning how to live within planetary limits while preserving the cultures that create knowledge, becomes part of the scientific project. A cosmos that allows knowers does not guarantee that knowing will continue. That is our responsibility, not the universe's. What then can physics not tell us? It cannot tell us what to value. It can inform our choices by revealing consequences and constraints, but it does not derive aught from is. It cannot tell us with certainty whether we are alone without data. It cannot pick a single story about origins when many are consistent with present evidence. These are not failures. They are reminders that science is a living practice tied to observation. Where observation is possible, science excels. Where it is not, speculation must be clearly labelled as such and kept on a leash. The good news is that new observations keep arriving. We are beginning to sniff the air of rocky exoplanets for hints of metabolism. We are learning to listen to gravitational murmurs from epochs we cannot see. We are pushing biology back toward its prebiotic roots, reproducing steps that might have occurred on an ancient Earth or on countless other worlds. And so the little word, because in we are here because we have to be, gains texture. It hides a cascade of because the low entropy beginning grants an arrow of time. Because inflation, or something like it, gave us a vast flat stage seeded with gentle ripples. Because the constants of nature permit long-lived stars and rich chemistry. Because non-equilibrium flows generate and sustain complexity. Because copying with variation allows selection to carve function from noise. Because symbiosis and energy abundance open paths to minds. Because minds given time and tools learn to understand. Each because is a place we can investigate, argue over, and test. If you've followed the thread from the first light to living minds, the next step suggests itself. We've spoken about origins and about meaning. We should ask how far this understanding can carry us into the future. Can we expect life and mind to persist as the universe changes, as stars die and darkness deepens? What do the long-term fates allowed by physics look like for civilizations that keep learning? In other words, having asked why we are here, we can now ask how long here can last, and what we might become if we continue to use knowledge as our way of being in the cosmos. If we're going to ask how long here can last, the honest place to begin is with the very ordinary star that gives us our span, the Sunday. It is a middle-aged main sequence star that has been quietly fusing hydrogen into helium for roughly 4.5 billion years, and will keep doing so for about another 5. But the future is not a static replay of the past. As the sun burns hydrogen in its core, the mean molecular weight increases, the core contracts and heats, and the luminosity creeps upward. That slow brightening matters. Well before the sun swells into a red giant, the extra light will push Earth's climate toward a runaway greenhouse. On conservative estimates, the biosphere has something like 1 billion years before the oceans begin to evaporate in earnest, and complex life as we know it becomes precarious. That sounds vast on human timescales and fleeting on cosmic ones. It is a reminder that even in a hospitable universe, habitability is a moving target. When the core hydrogen is exhausted, the sun's structure will change dramatically. The core will contract and heat, while a shell of hydrogen around it ignites. The outer layers will expand and cool, turning the sun into a red giant. The radius will swell to many tens of its current value. Whether Earth is engulfed outright or left as a scorched, airless rock depends on details of mass loss and orbital dynamics, but the difference is academic from the standpoint of life. Eventually, the outer layers will be lost to space, forming a glowing planetary nebula around the remnant core, which will settle as a white dwarf, an Earth-sized ember, supported by electron degeneracy pressure, slowly cooling over. Eons. That is the sun's quiet fate. It fixes a boundary on our local timeline. If minds like ours persist, they will not do so on an unchanged Earth under a yellow sun forever. They will have to adapt to move or to transform their energy needs. None of that implies despair. Stars are not rare, they are abundant, and many are better long-term furnaces than our Sunday. Small red dwarfs sip their hydrogen parsimoniously and can shine stably for trillions of years, thousands of times longer than the Sunday. If there are havens for life, far into the deep future, they are likely to be in the warm zones around such stars. That is one of the reasons astronomers are so eager to study the atmospheres of temperate rocky planets around cool dwarfs today. We are learning not only about our cosmic present, but about the energy landscape of the long tomorrow. Galactic dynamics adds another chapter. In roughly 4 billion years, the Milky Way and the Andromeda Galaxy will begin a slow, stately merger. The newspapers of that epoch, if there are newspapers, will not have headlines about stars. Colliding space between stars is mostly empty, but about tides reshaping the great star systems and about waves of star formation ignited as gas clouds are compressed. Over a few further billions of years, the two spirals will settle into a single more massive elliptical or lenticular remnant, sometimes nicknamed Milkomeda. For inhabitants of surviving planetary systems, the night sky will change profoundly arcs and plumes of starlight, then a new crowded central glow. The merger is not an omen of doom, it is part of the way structure evolves. If life has learned to travel or communicate across interstellar distances, by then such events become opportunities for migration and for distributing risk. Engineers like to ask the next question: can we shape our fate on stellar scales? In the thought laboratory, yes. A simple stellar engine, the Shkadov thruster, consists of a vast, slightly curved mirror that reflects part of a star's light back onto its surface, creating asymmetric radiation pressure, and with it, a tiny thrust. Over tens of millions of years, the thrust adds up, nudging a star and its bound worlds onto a chosen trajectory. More aggressive proposals imagine feeding stellar material into fusion jets, a Kaplan thruster to push the star more quickly. These are not plans for next century. They are proof of principle arguments that in a universe governed by known physics, even something as majestic as a star is not beyond an intelligent species' ability to shepherd, given absurdly long horizons and extravagant engineering. Energy collection is the other half of the equation. Freeman Dyson's famous thought, arraying collectors around a star to harvest a significant fraction of its light, has morphed into many variants: swarms of satellites, shells of reflectors, multi-layer matryoshka brains, with successive radiators running computation ever closer to the star's waste heat limit. The physics here is clean, you cannot break the second law. Every joule used for work or computation must be dumped as heat at some temperature, and the lower you can push that temperature, the more efficiently you can compute, or the more slowly you must run to keep within the cooling capacity of your radiators. That simple thermodynamic fact has two consequences. First, a civilization that harvests stellar energy at large scales will glow in the infrared. In principle, it could be seen from afar. Second, the most efficient place for computation is not close to the star, but as far from it as possible, where radiators can operate against the cold of space. That is one reason some thinkers suggest that advanced societies, if they exist, may gradually migrate outward in their planetary systems or into the dark between stars, not because light repels them, but because temperature differentials entice them. On still longer horizons, cosmology sets the stage. In our best description, the expansion of the universe is accelerating, driven by something that looks very much like a cosmological constant dark energy, with an equation of state parameter near -1. If that persists, the observable universe has a horizon, a boundary beyond which events can never influence us because the space between recedes too quickly. As time passes, distant galaxies not gravitationally bound to us will slip beyond that horizon and fade. The night sky will grow emptier. Star formation will dwindle as gas is used up or locked in remnants. The bright era will give way to a dimmer epoch dominated by low-mass stars and the long afterglow of stellar embers. The thermodynamic and informational consequences of an accelerating cosmos are profound. In a universe whose background temperature falls towards zero without bound, one can imagine a strategy of ever-slowing computation, stretching finite energy across an infinite subjective future by doing fewer and fewer irreversible operations per unit time. Dyson sketched such a possibility decades ago. But with dark energy that looks like a cosmological constant, the universe has a de Sitter horizon with a fixed tiny temperature and a finite information capacity within any horizon volume. Landauer's principle ties the minimal energy cost of erasing one bit of information to the ambient temperature. If there is an irreducible bath at a fixed temperature and a finite store of free energy in any region you can control, you cannot compute forever. You can only compute for a very long time. In that view, the deep future is not a theatre for infinite thought, but a long twilight in which energy is precious and horizons cloister what remains. Even in twilight, there are furnaces. Black holes, those ultimate sinks, can be turned briefly and with skill into sources. A rotating black hole stores enormous energy in its spin. Magnetic fields threading the surrounding plasma can tap that spin via the Blandford-Znajek mechanism powering jets that can run for millions of years in active galactic nuclei. On smaller scales, waves and particles can extract energy by superradiance, scattering off the ergosphere and leaving the hole with less spin. These are not solutions for eternity, but they are reminders that general relativity and electromagnetism together offer possibilities that Newtonian gravity does not. Much later, when accretion has dwindled and galaxies have dimmed, black holes themselves will leak energy through Hawking radiation. Stellar mass holes take an absurdly long time to evaporate. Numbers like 10 to the 67 years appear for a mass like the Sun's, while the most massive holes in galactic centers would persist for times with 90-something zeros. That era is too far beyond any practical planning to animate engineering, but it frames the grand dark energy sources, dwindle the characteristic timescale stretches, and the universe coasts toward a quiet end. There are uncertainties in this long view, and they are scientifically healthy to acknowledge. We do not know whether protons are truly stable. Experiments tell us that if they decay at all, the mean lifetime is at least around 10 to the 34 years, enormous compared to the ages we are used to. If protons decay, then ordinary matter is ultimately transient. If they don't degenerate, remnants and cold planets can persist for stupendous spans. We do not know whether dark energy is exactly constant. If it evolves even slowly, the far future could differ in important ways. In extreme hypothetical cases, if its density grew with time, the universe could end in a big rip. Observations today point firmly away from such drama, but the right scientific attitude is to keep measuring. The fate of everything we care about is entangled with a parameter we can, in principle, constrain. Against this vast backdrop, it's reasonable to ask whether meaning can persist. Physics does not supply purposes, but it sets possibilities and limits for agents that do. The same laws that forbid perpetual motion also forbid perpetual computation in a de Sitter universe. The same laws that make stars also make red dwarfs that last for trillions of years. If intelligence learns to thrive on modest power budgets, to copy itself across many niches and to reduce its dependence on specific planetary or stellar environments, then it can ride the universe's long decline much further than we might once have imagined. The most resilient strategies will look less like empires and more like ecologies, diverse, distributed, redundant and frugal. There is also a near-term moral hidden in the far future physics. Long before we concern ourselves with Dyson swarms and de Sitter horizons, we face the very local challenge of learning to live within the limits of one planet's energy and material cycles. That is not a distraction from the cosmic story. It is the prerequisite for having any future chapters. The sun will keep shining for billions of years, but our civilization's stability depends on matching our technologies to the thermodynamic realities of our environment in the next few centuries. In that sense, astrophysics and ethics shake hands. A species that cannot learn stewardship at home is unlikely to manage it across the stars. If we stitch this all together, a coherent picture emerges. The physical preconditions that made us possible, low entropy beginnings, gentle primordial ripples, long-lived stars, abundant chemistry also shape our prospects. The sun's brightening gives a window for flourishing and a deadline for local complacency. The galaxy's evolution provides new neighborhoods and new hazards. The deep fabric of the cosmos, with its accelerating expansion and its horizons, sets ultimate limits on information and energy. Within those limits, physics leaves room for ingenuity, for moving worlds and shepherding stars, for building quiet computers in the cold, for finding sustenance in places where gradients still flow. None of it is guaranteed. All of it is permitted. And notice the continuity with where we began. The quick answer, because we have to be, is not fatalism. It's a recognition that in a large enough menu of possibilities, regions compatible with life will be inhabited. The long answer, how long we can last, depends in part on how wisely beings within one of those regions learn to use the permissions physics grants. We will continue to test the early universe story by listening for primordial gravitational waves and by mapping the oldest light more cleanly. We will continue to test the late-time story by tracking the expansion and the growth of structure, and by looking for any whisper that dark energy is not constant. Meanwhile, we will keep exploring the nearby oasis of planets and the chemistry of life to see how common the first steps are. In the end, the universe offers a peculiar kind of hospitality. It does not care about us, but it allows us. It does not promise eternity, but it gives spans of time so generous that meaning can be made shared and refined. If the future holds minds under red suns, orbiting slowly, running computations with extravagant parsimony against a cold sky, then the same laws that lit our dawn will be guiding their dusk. And if it holds only us for a while on this one world around this one star, then the right response is the same: to learn to care for what we have and to treat knowledge as a way of being fully present in a cosmos that, against long odds, without intention, made room for beings who can ask why. If we keep following the thread, another essential question waits just beneath the surface of why are we here? Why is there any here made of matter at all? In the early universe, energy condenses into particles and antiparticles in nearly equal numbers. If perfect symmetry held, the young cosmos would have annihilated its matter and antimatter back into light, leaving almost no atoms, no stars, no planets, no chemistry, no us. And yet there is a tiny excess of matter over antimatter, about 1 part in 10 billion. That sliver is everything. The entire material content of the visible universe, the hydrogen in oceans, the carbon in leaves, the calcium in bones, traces back to that minute imbalance. We suspect it arose through a process called baryogenesis, in the rapid out of equilibrium conditions of the early universe, reactions that violate baryon number, the count of matterness, violate charge, parity, symmetry. So, the matter and antimatter are not treated identically, and proceed while the cosmos is changing fast can tip the balance. The recipe was laid down by Andrei Sakharov in the late 1960s. We have the shopping list. We do not yet have the full cookbook. Some versions of the standard model of particle physics nearly do the job but seem too feeble. Others extend the model with heavy neutrinos or new fields that could have swung the early cosmos toward matter. Neutrino physics, tiny masses, odd mixings, the possibility that neutrinos are their own antiparticles may hold a key. This is not an antique problem. Experiments today, from underground detectors that watch the faintest flashes to accelerators that compare the behavior of particles and antiparticles, are probing exactly the symmetries that a universe like ours must have broken. The line from that microphysical asymmetry to your cup of tea is direct. Even after matter wins its slight surplus, something else must shepherd that matter into the patterns gravity prefers. That something is dark matter. Without it, the primordial ripples measured in the cosmic afterglow would grow too slowly. Ordinary gas, tightly coupled to radiation in the beginning, would not collapse into galaxies early enough. Dark matter, feeling only gravity and perhaps very weak forces, begins to clump, first forming a scaffolding of invisible halos. Ordinary matter falls into those gravitational wells, and once it can cool and radiate energy away, settles into stars and disks and spirals. In that sense, we are here because the universe built a dark architecture early. We do not yet know what the bricks are. They might be new particles that were produced thermally in the first moments, so-called WIMPs, or ultralight fields, that behave coherently across galactic scales, axions, or sterile neutrinos, or something stranger. Each proposal makes subtle predictions how satellite galaxies should distribute themselves, how the centers of halos are shaped, how early stars formed. Telescopes and laboratory searches attack the question from both ends. As with baryogenesis, the scientific intuition is that the right answer will satisfy multiple constraints at once. It will fit in a broader theory of fields and symmetries and leave fingerprints in the sky. Once gravity has its way with the dark and the ordinary, the universe's story becomes a balance of feedbacks, a cosmic ecology. Star formation is not a calm, continuous drizzle. It is a bursty, self-regulating process. As gas collapses into stars, the massive ones shine intensely and live briefly, blasting their neighborhoods with radiation and winds. Some end as supernovae, stirring and heating their surroundings. In the most massive galaxies, central black holes accrete matter, and in doing so can launch jets and outflows that heat or expel gas on scales far larger than the black hole itself. These processes do not destroy structure, they sculpt it. They delay star formation in some places and trigger it in others. They control the pace at which galaxies use up their gas, which in turn controls the enrichment of space with heavy elements, the raw material for rock and water and life. So when you see a spiral galaxy glowing softly in a long exposure image, you are looking at the equilibrium outcome, of competing processes. Gravity pulling in feedback, pushing out, cooling, radiating away, energy dynamics, redistributing, angular momentum. Our existence is downstream of that balance. Heavy elements, the ones life leans on, arrive by multiple routes. Carbon and oxygen are synthesized in the cores of ordinary massive stars and spread by supernovae and stellar winds. The very heaviest, such as gold and uranium, appear to be forged largely in neutron-rich environments, created when compact stars merge events that, when they occur, light the sky in a kilonova and ring the fabric of space-time with gravitational waves. The point is not to romanticize jewelry metals. It is to emphasize that the periodic table is not supplied wholesale. It is built by time, by generations, by a sequence of furnaces and catastrophes. The chain from dark matter scaffolding to star formation to element manufacture to rocky planets is long but coherent. We are here because the universe had the time and the tools to run the chain. Even once a planet forms in a temperate zone, the difference between a sterile rock and an enduring biosphere depends on planetary physics that is at heart geology doing thermodynamics. Plate tectonics recycles crust and regulates carbon dioxide via the long carbon silicate cycle, buffering climate over millions of years. A dynamo in a liquid metallic core can build a magnetic field that shields an atmosphere from erosive stellar winds. Volatiles, water, carbon dioxide, nitrogen must be delivered and retained. Too little and you have a barren desert, too much or in the wrong form and you have a permanent steam bath. A large satellite can steady a planet's axial tilt, smoothing climate swings, though this is not a rigid requirement of life. Nature is inventive. None of these features is guaranteed on a random rock. Some may be common, others may be rarer. Our present exoplanet census reveals astonishing diversity super-Earths and mini-Neptunes that have no analogue here, tightly packed planetary systems, worlds that migrated inward or were scattered outward. The counselling here is humility. The rare Earth hypothesis may be too pessimistic. The mediocre Earth assumption may be too glib. Data will decide. If we change scale again and ask why the laws themselves look the way they do, another kind of answer emerges, this time from the mathematics of how complexity organizes itself across scales. The renormalization group devised to tame infinities in quantum field theory and later found to describe phase transitions in condensed matter tells us that when you coarse-grain blur out microscopic details and look at longer distances, systems flow toward fixed points where only a few parameters matter. The microscopic chaos washes out, universality appears. This is why very different liquids boil with the same critical exponents and why the thermal ripples in the afterglow have a simple spectrum. It is also why the effective field theories we use to describe nature at accessible energies are compact. Only a few relevant operators survive at long scales. So some of the simplicity in our laws may be less a reflection of a unique Platonic code and more a reflection of this mathematical mercy. Coarse graining makes the world legible. That does not trivialize the search for deeper unification, it frames it. If multiple microscopic stories flow to the same long-distance behavior, then the success of a simple law at our scale does not guarantee uniqueness underneath. Conversely, if we find a simple law that survives multiple tests across scales, we should treat it with respect. It is a fixed point in more than one sense. Symmetry knits together much of what we know. Noether's theorem, one of the crown jewels of theoretical physics, tells us that every continuous symmetry corresponds to a conserved quantity. Time translation symmetry gives energy conservation. Space translation symmetry gives momentum conservation. Rotational symmetry gives angular momentum conservation. Gauge symmetry's more abstract cousins underpin the interactions in the standard model. We break symmetries too, and in that breaking, masses arise and phases change. In the early universe, cooling can lead to phase transitions as fields settle into new configurations. If baryogenesis occurred at such a transition, the details of the symmetry and its breaking determined our material fate. Symmetry is not a decorative idea, it is a generator of necessity. And when we look for physics beyond the standard model to account for dark matter or neutrino masses or the matter-antimatter asymmetry, we often look for new symmetries and new ways to gently break them. One layer, more abstract, and we reach information. We have already seen how life is an information processing pattern. Physics too can be recast as constraints on how information flows. Landauer's principle links the erasure of a bit to a minimal heat cost. The holographic principle, inspired by black hole thermodynamics, suggests that the maximum entropy or information capacity of a region scales with its boundary area, not its volume. In some modern approaches, space-time itself is emergent from entanglement patterns in a deeper quantum description. These are not settled facts, but they are active research directions that connect the arrow of time, quantum theory, and gravity. If they are right, then "Why are we here?" will eventually include a sentence about why the universe has the information theoretic capacity and structure to host complex error-correcting patterns like life. Even if they are not the last word, they already give us a vocabulary for talking about laws as constraints on computation and communication, a vocabulary that links the first seconds of the universe to the workings of a cell and the operations of a mind. All of this baryogenesis, dark matter scaffolding, feedback sculpted galaxies, element factories, planetary thermodynamics, renormalization, symmetry information, is a long way of fleshing out that deceptively simple, quick answer. Because we have to be is not a shrug. It is an invitation to trace the chain of permissions. At each link, there is a place where a different outcome would have closed off the path. If CP symmetry had been perfect, no matter surplus. If dark matter were absent, no early halos. If feedback had been too violent or too feeble, galaxies either quenched or ran away. If heavy elements were rare, chemistry impoverished. If planets did not regulate their climates, stability lost. If the laws were not compressible across scales, no reliable science to guide technology. If information could not be stored robustly, no memory to accumulate. We do not need every dial to be tuned with exquisite precision. Nature is more generous than that. But we do need a corridor, and the evidence suggests we inhabit one. The last turn I want to take in this chapter is toward method because it underlies everything else. What makes these answers trustworthy is not that they are grand, it is that they are testable. We can look for the signatures of CP violation in the decays of mesons and baryons and in the oscillations of neutrinos. We can map the small-scale structure of dark matter halos by watching how they lens background galaxies and by counting satellite galaxies with future surveys. We can time gravitational waves from merging neutron stars and read in the glow of the kilonova the fingerprints of new elements being born. We can probe exoplanet climates and compositions and watch for cycles consistent with active geology. We can use the renormalization group to connect what colliders see at higher energies to what cosmology infers at lower energies. We can push quantum experiments that tangle ever more macroscopic objects and see whether space-time itself leaves a signature in the patterns of entanglement. Each test constrains the corridor, sharpens the story, and when we are lucky, surprises us into rewriting parts of it. So where do we step next on our walk? We have spoken about why, in terms of preconditions and permissions. We have traced the path from the earliest asymmetries to the latest minds. The next natural move is to go right to the edges of what we know and look outward and inward at once. Outward to the possibility that inflation is not the only beginning, that perhaps our bubble sits among many, and that selection on a vast stage explains the smallness of dark energy and the hospitality of physics. Inward to the quantum foundations that may in the end decide what many really means and whether probabilities in a cosmological context can be anchored to a unique coherent measure. In other words, let's turn our attention to multiverse logic and quantum interpretation and ask how the deepest why questions meet the most precise how questions at the frontier of modern cosmology. At the frontier where cosmology meets quantum theory, one simple sentence causes all the trouble in a universe that is the whole show, who is the observer. In laboratory physics, we cheerfully divide the world into a system that we describe with a quantum state and an apparatus that reads out a result. But for the early universe, there is no outside apparatus. There is only the universal wave function evolving by tidy linear rules. That is why quantum foundations are not a side quest for philosophy clubs, they sit right under our cosmological stories. If you want to understand multiverse logic, you must first be clear about what quantum mechanics says happens when possibilities meet reality. The basic ingredients are familiar. The Schrödinger equation evolves a state into superpositions of alternatives. Left alone, those alternatives can interfere. When a system becomes entangled with a vast environment, the air, the photons, the apparatus, the coherence between different alternatives is shredded. This process is decoherence. It does not pick a single outcome. It hides interference by dispersing phase information into countless environmental degrees of freedom. What it does give you is classicality, robust pointer, states that behave as if they were classical variables, because any superpositions of them are immediately decohered. In a lab, that's why a Geiger counter offers a definite click and not a smear of maybes. In cosmology, decoherence is why the quantum fluctuations of the inflaton field, the ones inflation stretches to astronomical scales, become the classical ripples we see as temperature blotches in the cosmic microwave background. As modes stretch beyond the Hubble radius during inflation, they enter highly squeezed quantum states. Tiny interactions with other fields and with the metric itself amplify decoherence. Interference dies. A definite pattern of density ripples is recorded on the sky. Quantum mechanics remains universal. Classical behavior emerges where redundancy and environmental entanglement make some records objective. That is the working bridge. What then counts as an outcome? One coherent minimalist answer is the Everett or many worlds interpretation. The wave function never collapses, it branches. When an interaction entangles a system with its environment in a way that decoheres alternatives, each alternative persists as a separate branch with no further interference between them. Under this view, measurement is just ordinary, unitary evolution seen from inside one branch. The contested point is probability. If all branches exist, why should you weight them by the Born rule, the square of the amplitude? Several routes try to show that you must. Decision-theoretic arguments say that a rational agent who knows branching will place bets as if the Born rule held. Invariance arguments emphasize symmetries of entangled states that force the same weighting. Typicality arguments tailored to cosmology treat observers as uncertain about which branch they occupy and derive the same frequencies. You can be unpersuaded by any specific route and still acknowledge the broad lesson quantum theory can be read as a complete branching dynamics, and decoherence explains why the branches feel classical. This matters for the multiverse because it tells you how to think about many in physics. There are at least two ways many appears. One is quantum branching within a single set of laws, Everett's multiplicity. The other is plurality in the laws themselves, as in eternal inflation, and the string landscape different pockets with different low-energy parameters. These two senses of many are often conflated. They need not be equivalent. Quantum branching gives you different outcomes under the same rules. Eternal inflation can give you different rules altogether in different bubbles. Yet in practice they meet because any cosmology that includes eternal inflation must also include quantum branching inside each bubble. And any quantum cosmology that tries to be globally complete must treat the whole inflating space-time as one gigantic entangled state. The upshot is that questions about measures how to count and weight possibilities have both an inflationary and a quantum face. On the inflationary side, the problem is literal infinity. In eternal inflation, new inflating volume is produced faster than old regions thermalize. The process never ends globally. Every kind of bubble that can form will form not just once, but infinitely many times. If you now ask what fraction of observers see X, you are dividing one infinity by another. The answer depends on your cutoff on how you regulate the infinity before taking a limit, and different seemingly sensible cutoffs give different answers. Global measures that slice the space-time by some notion of time face paradoxes. Some reward regions that expand faster the youngness bias. Some predict absurd dominance by rare events. Local measures that follow a narrow world tube, a causal patch, a fat geodesic, avoid some pitfalls, but introduce others like sensitivity to initial conditions you cannot observe. The goal is to define a measure that is well posed, gives finite stable answers, consistent with ordinary statistical reasoning, and not dominated by pathological observers. That last phrase is a reference to Boltzmann brain's hypothetical self-aware fluctuations that arise from thermal noise in a high-entropy environment. In a universe that lasts long enough in a quiescent state, such freak observers can in principle outnumber ordinary observers produced by stars and evolution. If your measure assigns most of the weight to them, you predict that typical observations are incoherent hallucinations, contrary to our experience. A viable cosmological measure must therefore be Boltzmann brain safe, which usually means that the regions where such fluctuations would dominate either do not exist, decay faster than they produce brains, or are heavily down-weighted by the measure. You can see the subtlety. A good measure is not a throwaway technicality. It decides whether the framework predicts our world or a nonsense world. That is why cosmologists care so much about the details. Quantum foundations offer two strategies for progress. One is the decoherent or consistent histories approach. Instead of lab measurements, you consider entire coarse-grained histories of the universe, sequences of propositions about ranges of values of fields at successive times. A set of histories is decoherent if interference between any pair of them vanishes. Only then can you assign classical probabilities consistently. The Wheeler-DeWitt equation, which in canonical quantum gravity replaces time evolution with a constraint psi equals 0, suggests that time is relational. One set of variables plays the role of a clock relative to others. In that setting, decoherent histories provide a way to extract probabilities for cosmological observables without appealing to an external observer. They do not magically solve the measure problem, but they replace some of its ad hoc cutoffs with a principled criterion: only histories that decohere cleanly should be counted, and the quantum state Hartle-Hawking's no-boundary wave function, or Vilenkin's tunneling wave function, for example, supplies weights. Those two proposals for the initial state try to do something audacious: derive the prior over universes from a simple boundary condition on the wave function. In the no-boundary idea, one computes a path integral over compact Euclideanized geometries that cap off smoothly, no initial singular edge, then analytically continues to Lorentzian time. The result is a psi that assigns higher weight to some classical histories than others. In the tunneling proposal, the universe nucleates from nothing in a specific semi-classical sense, favoring expanding histories. Both can be married to inflationary dynamics. The hope is that one of them, or a cousin, will pick out initial conditions that both explain why inflation starts and produce a distribution over observables curvature. The amplitude and tilt of primordial ripples, the value of dark energy, that matches what we see without ad hoc assumptions. This is a live research program rather than a finished book. The promise is clear replace, because we picked this prior, with because the quantum state of the universe demands it. A different quantum-informed route approaches the multiverse from the information side. Holography, the insight sharpened in anti-de Sitter contexts that the information content of a region scales with its boundary area, hints that a universe with a cosmological horizon like de Sitter space has a finite information capacity. If so, then eternal inflation may not produce a countably infinite banquet of distinct independent regions in the naive way. Instead, there may be redundancies and constraints that cut down the sample space. Ideas like horizon complementarity suggest that physics inside a horizon has a self-contained description that does not require double-counting degrees of freedom elsewhere. None of this has been welded into a universally accepted measure, but it changes the flavor of the puzzle. Instead of inserting a cutoff by hand, you hope to derive one from the microscopic accounting of states. Meanwhile, the same decoherent story that classicalizes density ripples during inflation has a cousin in ordinary experience called quantum Darwinism. The environment does not merely decohere superpositions, it redundantly records certain stable states, pointer states, so that many independent fragments of the environment carry the same information. That redundancy is what makes facts objective. Many observers can sample different photons and agree that the pointer points to 5. In cosmology, the environment that imprints redundancy includes long wavelength gravitational perturbations and ubiquitous radiation fields. The usefulness of this lens is conceptual clarity. It says you do not need a mysterious collapse to get the classical world you measure. You need robust records proliferating in the environment. The same mechanism that renders our instruments trustworthy rendered the early universe's fluctuations classical long before stars were born. Where do these threads touch observation? In several places. If no boundary style initial conditions weight smoother, universes more heavily, you expect a near-flat geometry and a spectrum of primordial ripples close to scale invariant, the broad features we do see. More specific predictions, for example, a small preference for a particular range of the curvature, perturbation, amplitude, or subtle correlations between large-scale modes, are harder to extract cleanly and compete with cosmic variance. But they are being pursued. If eternal inflation is correct, bubble collisions could leave circular features or specific statistical anisotropies in the microwave background. Systematic searches have placed strong limits on such signatures. Non-Gaussianity tests already rule out many exotic inflation models. Continuing null results push us toward the simplest single-field slow-roll territory. On the quantum side, tabletop experiments that entangle ever larger masses interferometry with macromolecules and proposals to witness gravity-mediated entanglement probe whether space-time itself participates in quantum mechanics in the way we expect a foundational check that matters when you lean on quantum cosmology. A theme in all of this is typicality. You never compute the probability of this universe, only distributions over observables, and you then assume you are not in an astronomically atypical location in that distribution. In standard statistics, this is uncontroversial. You would not expect to pick the one hydrogen atom in the sun that is moving at 1,000 times the thermal speed. In cosmology, it demands care because of selection effect. If life requires a narrow range of dark energy, then observers will find themselves in that range, even if it is very rare overall. That is the weak anthropic principle. It is a filter, not a cause. Used with discipline only when you have a prior distribution from a concrete theory, and only to condition on necessary preconditions, it can be predictive. Used loosely, it slides toward just so stories. The difference is whether the multiverse is a way to test models by linking them to data, or a way to excuse any outcome after the fact. The scientific value lies entirely in the former. Let me connect this back to the arrow of time because it closes a conceptual loop. Decoherence requires an environment that starts in a low entropy state relative to the system so that records can be made. The early universe provided exactly that, a low gravitational entropy background in which new redundant records could be written as structure formed. In turn, those records fossilized in photons, in dust, in the orientations of spins, and the shapes of ripples are why we find a world with a reliable past. Quantum theory alone does not give you an arrow, cosmology does. That is not an add-on. It is a demonstration that our deepest interpretive questions are entangled with the universe's boundary conditions. Where does this leave? The headline question, why are we here, leaves it sharpened. If a sound quantum cosmological theory selects a simple initial state that generically yields inflation, a near-flat geometry, a small positive dark energy, and the spectrum of ripples we measure, then much of the tuning dissolves into dynamics. If the same framework implies a multiverse of pocket universes with a distribution of low-energy constants, then selection effects can explain why we observe values compatible with chemistry and long-lived stars. If, on the other hand, future measurements find a decisive departure, a large, evolving dark energy, primordial non-Gaussianity of a kind inconsistent with any simple inflation, spatial curvature significantly different from zero, then we will return to the blackboard and revise. In both cases, the path is empirical. The deepest why questions acquire meaning, because we can point to numbers on the sky and in the lab that they must respect. The next natural doorway is a laboratory where quantum theory, gravity information, and thermodynamics collide with unusual clarity black holes. They radiate as if they have a temperature. They carry entropy proportional to horizon area. They seem to destroy information, and then under deeper scrutiny, to return it in scrambled form. The page curve that rises and then falls the island. Ideas that rescue unitarity, the holographic dualities that trade geometry for quantum entanglement, all of these threads feed back into how we think about measures, horizons, and the ultimate information capacity of the cosmos. If the universe is a place where meaning emerges from matter because records can form and persist, then black holes are the ultimate tests of what counts as a record. Let's walk there next to the edge of the horizon and ask how a hole that looks like perfect forgetfulness becomes a book that with enough patience returns every story it has swallowed. Black holes are where the neat linear narratives of classical physics knot themselves into riddles, and where quantum mechanics, thermodynamics, gravity, and information theory are all forced to speak the same language. Start with the classical picture, take enough mass and squeeze it tightly enough, and gravity corrals light itself. The boundary beyond which escape is impossible is the event horizon. From the outside, a black hole is simple. It has mass, spin, and electric charge. Nothing else you can measure survives. This no-hair simplicity is so stark that it sounds like an end to stories. How can something that's forgetful also be the key to how the universe remembers? The first hint that horizons are not blank walls came from thermodynamic analogies. In the early 1970s, Jacob Bekenstein argued that a black hole must carry entropy, an accounting of how many microstates are compatible with its gross appearance, because otherwise you could cheat the second law of thermodynamics by throwing your messy high entropy object into a hole and watching entropy disappear from the universe. To keep the second law safe, the hole's entropy had to grow when you fed it stuff. He went further and proposed that the entropy is proportional to the horizon area. Stephen Hawking then did something audacious. He treated the quantum fields living on a fixed black hole background and showed that what we call empty space near the horizon is not so empty after all. Virtual particle pairs that constantly flicker into and out of existence are pulled apart by the horizon's geometry. The result, when calculated carefully, is that a black hole radiates with a thermal spectrum as if it had a temperature and slowly loses mass. The formulae stripped of constants say the temperature is inversely proportional to the hole's mass, and the entropy is 1/4 of the horizon area measured in Planck units. A black hole, the most gravitational of objects, is also a hot object with an enormous heat content. That insight turns the no-hair slogan on its head. If a black hole has entropy, it has hidden microstates degrees of freedom we cannot see directly in the classical description. Hawking's calculation, however, also opened a paradox. Suppose you start with a pure quantum state, perfectly well defined in principle, and collapse it to form a black hole. Hawking radiation emerging from the horizon is thermal. If the whole evaporates entirely, the end product seems to be a bath of featureless heat, a mixed state with no trace of the detailed information that fell in. But quantum mechanics insists on unitarity. Pure states must evolve to pure states. Where did the information go? There are several possible ways out, and over the decades, each has had its advocate. One is to throw quantum mechanics under the bus and accept non-unitary evolution. That option has never found a friendly mathematical home. It is hard to make it consistent with the precision of ordinary quantum experiments. Another is to keep unitarity, but break the equivalence principle at the horizon. Perhaps an energetic curtain or firewall forms, destroying infalling information and later releasing its detailed pattern in the outgoing radiation. That solves bookkeeping at the price of making horizons violent and of violating the comfortable assumption that for a large black hole crossing the horizon feels locally uneventful. A more conservative, and today the dominant thread, keeps both unitarity and smooth horizons by rethinking how and where information is stored and recovered. To see that thread, picture the entropy of the emitted radiation as a function of time. If Hawking's original calculation were the last word, the radiation entropy would rise steadily until the whole vanishes, because each new photon looks thermal and uncorrelated with the rest. Don Page pointed out that if evaporation is actually unitary, that curve must bend initially. The radiation entropy grows. But about halfway through the lifetime, the page-time correlations between earlier and later quanta become significant, and the fine-grained entropy starts to fall, ending at zero when all information has escaped. This page curve is what you expect from any unitary quantum system that sheds parts of itself. Early emissions look thermal. Later emissions are subtly encoded with the early ones. But where do those correlations come from? One answer is that the black hole is not a passive furnace. It is an extraordinarily efficient scrambler. The Hayden-Preskill thought experiment captures the idea. Throw a diary, some new quantum information into an old half-evaporated black hole. Intuition says you will never see the diary again. Quantum information theory says otherwise. If the whole is a fast scrambler, the diary's quantum state is rapidly mixed into the whole's degrees of freedom. And after a short scrambling time, the details begin to leak out, encoded in the correlations among the outgoing Hawking quanta. In principle, with a perfect quantum computer and access to enough of the radiation, you could reconstruct the diary. Practically impossible, yes. Conceptually crucial, also yes. It shows that there is no contradiction between thermal-looking radiation and unitarity if the radiation is only apparently thermal until you examine the right joint observables. Still, hand-waving about scrambling is not a derivation. The modern leap came from two directions that converged beautifully. The first is holography. In certain universes with negative curvature anti-D, Sitter space, a theory of gravity in the bulk is exactly equivalent to a quantum field theory, with no gravity living on the boundary. This adds divided by CFT duality is a dictionary, not a metaphor. In that setting, a black hole in the bulk corresponds to a hot state in the boundary theory, but boundary evolution is manifestly unitary. There is nowhere for information to go. That alone strongly suggests that black hole evaporation is unitary at the fundamental level. Holography then goes further. It shows how bulk geometry emerges from patterns of entanglement in the boundary, and it frames bulk reconstruction as a kind of quantum error correction. Information inside the bulk is encoded non-locally in the boundary degrees of freedom. You cannot point to a single place in the boundary that has the bit you need a large enough slice. That is exactly the kind of non-local encoding that makes information hard to destroy and hard to access without the right collective measurement. The second direction used semi-classical gravity itself, but allowed it to be more adventurous. Hawking's calculation follows a single saddle point of a gravitational path integral. In the last few years, people found that when you compute the fine-grained entropy of Hawking radiation carefully, using a generalized entropy that adds the area term to the quantum entropy of fields, you must extremize that quantity over possible surfaces, the quantum extremal surfaces. Doing so sometimes reveals an island, a region inside the black hole, that must be included as part of the radiation subsystem when you compute its entropy. If that sounds odd, that's because it is. It says that the correct bookkeeping of what counts as outside becomes state-dependent and subtle in quantum gravity. But when you include islands, the entropy of the radiation follows a page curve, automatically rising at first, then turning over and falling without ever giving up semi-classical control in regimes where gravity is weak. The technical objects that make this work in the path integral are replica wormholes, new saddle points that connect multiple copies of the geometry used in a standard trick for computing entropies. In solvable toy models, and in higher dimensional setups with strong hints from holography, including these saddles, makes semi-classical gravity agree with unitarity. If information does escape, where was it stored while the whole still existed? Holography suggests a non-local answer. It was never in one place. The bulk interior, what an infalling observer experiences as a smooth continuation of space, corresponds in the boundary description to particular entanglement patterns across large regions. That perspective inspired the slogan ER equals EPR. Perhaps a wormhole, an Einstein-Rosen bridge, is literally a geometric avatar of entanglement, Einstein, Podolsky, Rosen. In an eternal two-sided black hole, the two exteriors are entangled in a special way called a thermofield double, and the geometry includes a bridge connecting them. You cannot walk through it, it is non-traversable. But a clever twist, adding a small time-dependent coupling between the two boundary systems, injects a pulse of negative energy into the bulk and makes the wormhole briefly traversable. In the boundary language, this looks like a quantum teleportation protocol. In the bulk, a particle thrown in from one side pops out on the other. That experiment, carried out numerically in small quantum simulators and probed conceptually in laboratory systems, is not opening a hole in space-time in the science fiction sense. It is an existence proof that information can be moved in gravity in ways that mirror ordinary quantum information tasks, and that space-time and entanglement are two faces of one coin. If this picture is roughly right, what happens to the firewall worry? The paradox that led to firewalls rested on a tug-of-war over entanglement. Hawking's semi-classical picture says each outgoing quantum is entangled with a partner that falls behind the horizon. Unitarity says it must also be entangled with the early radiation if the whole state is pure at the end. But in quantum mechanics, a system cannot be maximally entangled with two independent others. At once entanglement is monogamous. Something has to give. The island calculation resolves the tug by redrawing the parties. After the page time, the correct division of the Hilbert space assigns part of what you naively called the interior to the radiation's entanglement structure. The late quantum is entangled with the appropriate interior mode, but that interior mode is encoded in the early radiation in a highly non-local way. No rule is violated. The seeming conflict arose from an oversimplified split of degrees of freedom. From the vantage of an infalling observer, nothing dramatic happens at the horizon. From the vantage of a godlike accountant who has access to the entire radiation field and can do exponentially hard computations, the interior can be reconstructed. Both descriptions are consistent because neither single observer can hold all descriptions at once without contradiction. That truce goes by names like black hole complementarity and quantum error correcting encoding. Where does all of this touch observation? Not at the Hawking temperature of an astrophysical hole. That radiation is far too cold to catch. But there are several windows. Gravitational wave astronomy lets us listen to the ring down of newly merged black holes, the dying tones of vibrating horizons settling to simplicity. The pattern of those tones tests the no-hair theorem. If extra hairs exist, the spectrum shifts. So far, the tones match general relativity's expectations. Imaging the near-horizon environment with very long baseline interferometry, the Event Horizon Telescope's portraits probes how light bends and how plasma swirls in the strong gravity regime. Observations are consistent with the classic black hole geometry. On the quantum side, analog systems fluids, Bose-Einstein condensates optical setups can mimic horizons and have produced thermal emission in line with Hawking's logic. They do not prove black holes radiate, they show that the underlying kinematics is robust. And in the laboratory of theory, holography and solvable models keep paying off, we can literally compute the entropy of certain black holes by counting microstates in string theory. We can watch a page curve emerge in controlled settings. We can design teleportation, like couplings that realize traversable, wormhole behavior in dual descriptions. Why should any of this matter for our bigger question, why are we here? Because black holes are the universe's most extreme record keepers. Entropy counts records. Records make memory. Memory allows cause and effect to accumulate into history. The same area law that assigns entropy to black hole horizons hints at a general rule: the information content of a region of space-time is limited by its boundary. That is the holographic principle in embryo. If it is true not only in anti-de Sitter universes, but in ours with positive dark energy acceleration, then our cosmic horizon carries a finite entropy too. That would mean there is a maximal information capacity to our patch's ceiling on how much distinct pattern can be etched into reality here. We do not yet have a clean holographic jewel for de Sitter space, but the steady pressure of new ideas, the island formula, gravitational path, integrals with new saddles, the entanglement geometry dictionary suggests that even our accelerating universe may obey similar bookkeeping. And if the cosmos is fundamentally an information processing arena with finite budgets and error-correcting encodings, then it is not surprising that robust error-correcting patterns like life and mind can arise and persist within those budgets for a time. There are open ends everywhere you look, which is good science rather than bad news. How microscopically do black hole degrees of freedom realize the area law in general? Space-time's not just in carefully supersymmetric corners. Can we generalize the island story from controlled models to fully realistic evaporation without any ad scaffolding? Will we ever see indirect hints of quantum gravity and astrophysical data, tiny deviations in ringdown, correlations in gravitational waves, new particles linked to black hole microphysics? On the cosmological side, can we build a convincing holographic description of universes with positive dark energy? And will that description clarify the measure problem that eternal inflation posed? Each question is a chance to turn the quick answer we started with into a web of tested statements. And because we have kept our footing in testable physics, we can loop back from the horizon to the home we started from. If space-time itself is knitted from entanglement, if horizons are books rather than walls, and if information is never destroyed but only scrambled and encoded, then the cosmos is not a stage that forgets its play. It is a patient accountant of what happens. That is why the second law wins, why the arrow of time is real, and why small local agents can build memories and models that work. In a sense, the universe's deepest austerity areas limit information, horizons radiate, no single observer sees every story turns out to be the same set of constraints that makes meaning possible. They keep physics honest, and they give us a way to be here to learn and to project forward. Where do we walk next? One natural path leads from black hole thermodynamics back to cosmology's first seconds. If horizons are hot and carry entropy, the early universe's horizons did too. Quantum fields in rapidly expanding space-time produce particles. Structure is seeded by squeezed quantum fluctuations. The same tools that tame the paradox at the edge of a black hole help sharpen our picture of inflation's initial conditions and the arrow of time. Another path runs inward to the laboratory scale, where entanglement, error correction, and complexity can be tested and engineered directly. Both paths converge on a single promise: the more we understand information in the presence of gravity, the more legible why we are here becomes not as fate but as the lawful outcome of a world that keeps records and allows patterns to persist. If horizons are books rather than walls, then the early universe is a library in the act of being written. The same physics that makes a black hole warm and forgetful in just the right way also tells us that an expanding space-time has a temperature, carries entropy, and creates particles. In the first fractions of a second, the universe was not an empty stage waiting for actors. It was a restless quantum field, amplifying certain fluctuations, freezing them into place, and laying down the scaffolding on which every galaxy would later hang. Start with a clean picture. During inflation, space expands almost exponentially. Quantum fields, especially the one driving inflation, are never perfectly still. They jitter. In ordinary circumstances, those jitters are tiny and ephemeral, but inflation stretches them. A ripple that begins life smaller than an atom can be blown to astrophysical size in a blink of cosmic time. Once a ripple's wavelength becomes larger than the horizon, the distance over which signals can travel during that epoch, it effectively drops out of causal contact with itself. Interference fades. The ripple's amplitude stops oscillating and freezes at a classical value. Later, long after inflation ends and the universe fills with hot radiation, those frozen ripples re-enter the horizon as gentle over and under densities. Gravity amplifies them, pressure counters them, and the two together set up the primordial sound waves whose faint rings we read in the cosmic microwave background and in the galaxy distribution today. There is something wonderfully universal about this mechanism. The details of whatever high-energy physics lives at unimaginable scales are hidden from us, but the way long wavelengths are squeezed and frozen is almost model-independent. That is why the imprint of inflation looks simple, nearly scale-invariant ripples with a slight tilt, almost Gaussian statistics, and correlations that match an origin in sound waves. In this sense, the early universe is the most accessible quantum system we will ever have, and we have measured it with exquisite precision by turning the sky into a detector. Of course, inflation must end. The potential energy that drove the ultra-rapid expansion is converted into a thermal bath of particles and radiation, in a process bluntly called reheating. Here microphysics matters again. The couplings between fields determine how quickly and into what species that energy is dumped. Sometimes the decay is gentle and perturbative. Sometimes it is explosive with resonances that momentarily overproduce certain particles before settling. Either way, what follows is hot Big Bang evolution now, with a very particular set of initial conditions: flat geometry, the uniform bath of radiation, and those faint, spatially coherent ripples everywhere. Because the early universe was hot and expanding, it also had horizons. And horizons in quantum field theory come with temperatures. A uniformly accelerated observer perceives a bath of particles, the Unruh effect. In a de Sitter, like expansion inflation's close cousin, there is a Gibbons-Hawking temperature associated with the cosmological horizon. These are not metaphors, they are statements about vacuum fluctuations and what counts as particles when space-time itself is not static. The analogy with black holes is not perfect. The horizons are different in detail, but the kinship is real. Geometry determines which modes are accessible to an observer, and quantum fields fill the inaccessible region with entropy. This is one reason why the information theoretic language fits the early universe so well. What looks like randomness in the primordial pattern is not ignorance, it is the concrete quantum origin of the initial conditions. That same language helps with an old anxiety: why were the initial conditions so special? We said earlier that the early universe had extraordinarily low gravitational entropy. Inflation does not by itself solve that. In many models, you still need a patch smooth enough to start. But inflation turns a modest requirement into an abundant outcome. Given any region large enough and flat enough to inflate conditions that might be generic in some quantum gravitational picture, it will erase memory of earlier clutter and lay down a graceful, almost scale-free pattern. There are proposals like the no-boundary idea that try to put this on firmer footing: the quantum state of the universe preferentially weights smoother beginnings. If such a law is right, then our low-entropy start is not an unexplained gift. It is the most probable classical history conditioned on the simplest quantum boundary condition. That is not settled, but it is testable in spirit. A framework that picks initial conditions must imply distributions for observables, the amplitude of the primordial ripples, the overall curvature, even the value of vacuum energy that we can compare to data. The other direction from horizons leads inward to a surprising protagonist: complexity. Not complexity in the everyday sense of complicated, but a technical measure borrowed from quantum information theory. Roughly, the circuit complexity of a quantum state is the minimal number of simple operations gates needed to build it from a reference. For generic interacting systems, complexity tends to grow and keep growing, long after more familiar measures like entropy have saturated. In the theoretical worlds where gravity and quantum field theory are precisely dual, black holes are the fastest scramblers and the most voracious complexity engines. The geometry behind a horizon grows in ways that seem to mirror the growth of complexity in the dual quantum state. Conjectures with names like complexity equals volume and complexity equals action make this intuitive link concrete. Whether or not those exact formulas are right in our universe, the motif is suggestive. There is a second law-like arrow in the growth of complexity, and gravity appears to know about it. Why dwell on this? Because it hints at a unifying picture of time's arrows. One arrow is thermodynamic entropy increases. Another is cosmological. The universe expands and structure forms from a low entropy beginning. A third, more recently appreciated, is computational. The typical quantum state of a large system marches toward higher complexity. These arrows point in the same direction in our world. The deep reason might be that the microphysics and the macroscopic geometry are two descriptions of one underlying flow: entanglement and complexity, weaving space-time at the same time that space-time guides how entanglement and complexity can grow. That is still speculative, but it is a fruitful speculation because it suggests new questions we can sharpen. Can we measure complexity, even indirectly, in many body systems in the lab? Can we catch gravity counting gates in a way that shows up in gravitational waves or black hole ringdowns? Can we export the error-correcting picture of holography to cosmology, where there is no nice boundary and the horizon is cosmological rather than ADS? The early universe also forces restraint. Inflation is a mechanism, not a monolith. There are cousins and competitors. Ekpyrotic and bouncing models replace the ultra-rapid expansion with a period of slow contraction followed by a bounce, smoothing the universe by damping anisotropies rather than stretching them away. These scenarios make different predictions for the spectrum of primordial gravitational waves and for the pattern of non-Gaussianity. Cyclic ideas, including Penrose's conformal cyclic cosmology, imagine aeons glued end-to-end with physics at the remote future of one aeon, setting the initial conditions for the next in a mathematically elegant way. None of these frameworks has yet matched inflation's detailed parameter-light agreement with the data. But the right posture is not dogmatic. We should keep asking how to tell them apart cleanly. What precise shape of B-mode polarization, what correlation across scales, what subtle residues in the microwave background would point decisively one way or another? That is science. At its best, big ideas, sorted by small features. Zooming back down to Earth for a moment, it's striking how much of this grand story has immediate tactile analogues in the lab. Quantum squeezing, the process that inflation performed on long wavelengths, is used every day to beat noise limits in precision measurements, including the interferometers that detect gravitational waves from merging black holes. Decoherence, which classicalized the sky, is the bane and backbone of quantum computing. You fight it while also relying on it to make measurement outcomes robust. Error correction, which seems to be built into the way holography hides bulk information across a boundary, is what allows fragile quantum information to be stabilized against noise. Experiments that entangle small mechanical resonators, levitated nanoparticles, or cold atomic clouds probe whether gravity itself participates in quantum correlations as it should. These are not stunts, they are increments toward a single narrative in which the same principles carry from the earliest fraction of a second to the quiet hum of a dilution refrigerator. There is one more connection to why are we here that becomes clearer in this information-first lens. We spoke before about selection. In a vast space of possibilities, observers naturally find themselves in regions where observation is possible. That sounds circular until you turn it into a quantitative statement, given a distribution of constants and initial conditions generated by a well-defined theory condition on the existence of long-lived stars, heavy elements, and free energy flows, and ask what values are typical in that conditioned ensemble. The small, positive, dark energy that we measure is exactly the kind of value that passes this filter. Much larger values would sterilize structure. But there is a deeper filter operating right alongside information capacity. A world that allows error-corrected records to form and persist is a world where observers can learn, remember, and build. If holography's area law is a general rule, then any finite region's capacity is finite. That does not cheapen meaning, it anchors it. Life and mind do not need an infinite canvas. They need a canvas that holds its pattern long enough for selection and culture to work. The early universe supplied that long coherence lengths a uniform bath and the delayed onset of acceleration so that galaxies could assemble and persist. None of this answers a philosophical why in the teleological sense. The universe is not trying to produce us, but it does refine the scientific why into a chain with fewer arbitrary links. Low gravitational entropy at the start is not left as a coincidence. It falls from a simple quantum boundary condition if that program succeeds. The delicate-looking constants are not written off as miracles. They are outcomes in a distribution filtered by the requirements of structure and memory. Horizons do not hide mysteries behind metaphors. They are thermodynamic information, theoretic objects whose temperatures we can calculate and whose entropies we can count. Black holes do not destroy information. They scramble and encode it, and in doing so they teach us how space-time itself might be an error, correcting code. Inflation is not a slogan, it is a set of statistical predictions we have checked and will keep checking with new light and sharper maps. So where do we walk from here? Having stood at the horizon of a black hole and in the barely begun universe at once, the next natural step is to look squarely at the places where our ignorance is not romantic but specific. What precisely is dark matter made of, given that its gentle gravity choreographs structure from the start? What precisely is dark energy, given that its tiny positive pressure now sets the cosmic tempo? What precisely are neutrinos up to, and did their odd behavior help tilt the cosmos toward matter over antimatter? Each of these questions threads through the story we've been telling. Each admits concrete tests, direct detection in the lab, subtle lensing signatures in the sky, spectral fingerprints in the light of distant galaxies, timing patterns in pulsars, correlations in the polarization of the oldest light. And for balance, we should turn the lens homeward again to ask how a species that understands horizons and early universe squeezing can use that understanding to make better choices in the narrow band of time that is actually ours. Physics will not tell us what to value, but it will tell us what is possible and what is not, what scales matter, and how fragile certain gradients are. The cosmos has already been generous. It has given us time under a steady sun, a planet with self-repairing climate cycles, and a sky that still carries the fossil pattern of its birth. If we keep learning, keep testing, and keep treating knowledge as a practice rather than a possession, the chain from first fluctuations to curious minds may yet lengthen. Let's continue then with the unglamorous but decisive next. Links the dark components that make up most of the cosmos by mass energy and yet remain invisible to our senses. They are not decorations on the story, they are the scaffolding and the set lighting. If we can name them and weigh them properly, the because in because we have to be will tighten from a broad permission to a set of specific check necessities. Let's turn the lights up on the two invisible actors that set the tempo of the cosmos, dark matter and dark energy. Together they make up about 95% of the energy budget of the universe, yet neither shines, rattles or clinks in our detectors the way ordinary matter does. That sounds like an admission of ignorance, but it's actually the starting point of a very precise story, because gravity lets us weigh what we cannot see. Dark matter first announces itself in motion. Spiral galaxies spin fast, too fast, if all that held their stars was the gravity from the luminous disk. The stars on the outskirts move as if they are embedded in a massive, unseen halo that extends well beyond the visible spiral. Clusters of galaxies tell the same tale. Galaxies orbit quickly inside a cluster's potential well, and the hot gas between them is too energetic to be confined by the gravity of the visible galaxies alone. Light itself testifies under oath. When background galaxies are lensed distorted into arcs and smudges by foreground mass, the lensing pattern maps where the mass is not where the light is. Over and over again, the maps agree there's a dominant transparent scaffold of matter, whose only strong friendship appears to be with gravity. Perhaps the most striking photograph of this scaffold is a pair of colliding galaxy clusters, nicknamed the bullet cluster. The hot gas in the collision ordinary matter slams together and slows glowing in X-rays. The mass revealed by gravitational lensing sails on with the galaxies. The mass and the baryonic gas separate. That's a difficult picture for any theory that tries to do away with dark matter entirely by modifying gravity. It looks exactly like two fluids, one collisional gas and one that barely notices itself, dark matter passing through each other. Cosmic archaeology adds more evidence. The tiny ripples in the cosmic microwave background, CMB, the oldest light we can observe, encode the composition of the universe when it was a few 100,000 years old. The pattern of peaks and troughs in that sky spectrum tells you how much ordinary matter there is, how much dark matter, and how they danced with radiation. The numbers that best fit the CMB agree with the numbers you get when you count galaxies and measure their clustering billions of years later. Dark matter was already present in the early universe, quietly seeding structure before ordinary matter could clump. So what is it? The honest answer is we don't know yet, but we have hypotheses, and we are testing them ruthlessly. One classic idea is that dark matter is a new particle that was once in thermal equilibrium with the hot early universe and then froze out as space expanded the weakly interacting massive particle, or WIMP. If that story is correct, there should be a tiny chance that a WIMP bumps into a nucleus on Earth and leaves a whisper of energy. We've built exquisitely quiet underground experiments, enormous vats of liquid xenon crystal arrays cooled to a fraction of a degree above absolute zero to catch such whispers. So far, the silence is telling. Detector after detector has pushed the plausible interaction strength, lower sculpting the WIMP landscape into a narrow strip rather than a broad plane. Another path leads to axions, very light particles originally proposed to solve a puzzle in quantum chromodynamics. Actions could be produced copiously in the early universe and drift through galaxies today as a cold classical field. They couple so feebly that they pass through planets as if they were fog, but they can convert into photons in the presence of a magnetic field. That gives you a hook. Haloscope experiments place resonant cavities and high-Q circuits inside strong magnets, and listen for a faint excess of radio frequency photons as the axion field tickles the cavity. Others point powerful magnets at the sun helioscopes, hoping to turn solar axions back into X-rays. New ideas use dielectrics, cleverly shaped arrays, even ferromagnets, and nuclear spins. The parameter space is wide, the search is methodical, there are more exotic options. Ultralight fuzzy dark matter with masses around 10 to the minus 22 electron volts would have a de Broglie wavelength as large as a galaxy core, smoothing out small-scale structure and perhaps addressing tensions between simulations and observations of dwarf galaxies. Self-interacting dark matter particles that feel a dark force among themselves could alter the inner density profiles of halos. Sterile neutrinos. Neutrinos that don't even feel the weak force could make up some or all of the dark matter if they have keV scale masses and the right production history. Each candidate leaves different fingerprints in the number and internal structure of small galaxies, in the way mass is distributed at the centers of halos, in subtle imprints on the CMB, or in spectral lines from decays. Astronomy and laboratory physics meet in the middle. If a candidate is real, it must satisfy both sets of constraints. There is a competing impulse with a long pedigree, perhaps. Gravity itself is different on galactic scales. Modified Newtonian dynamics MOND and more formal relatives try to change the force law at low accelerations so that galaxy rotation curves flatten naturally. These frameworks can fit individual galaxies remarkably well with a single extra parameter, which is intriguing. But when you step out to cosmological scales, CMB peaks, large-scale structure cluster dynamics, the same modifications struggle unless you then add back something that looks very much like dark matter. The weight of evidence, especially when you consider the early universe, still favors a new substance over a new law. That verdict could change with decisive data, but for now the invisible scaffold behaves like matter. Dark energy is stranger. It is not a substance that clumps into halos. It is an energy associated with space itself, observed through its effect on the expansion of the universe. In the late 1990s, two teams used Type Ia supernovae as standardizable candles to trace how the expansion rate changes with time. The distant supernovae were dimmer than expected. In a decelerating universe, they were farther away, implying that cosmic expansion has been accelerating for the last few billion years. That acceleration is now seen in multiple ways. In the pattern of baryon acoustic oscillations, ancient sound waves frozen into the galaxy distribution, in the integrated sacs, Wolf effect, large-scale CMB photons, gaining energy as gravitational potentials evolve in an accelerating background, and in weak gravitational lensing of galaxies over cosmic time. A simple model fits the data astonishingly well. A cosmological constant, Einstein's lambda, with an equation of state parameter W equal to -1, pressure negative enough to pull the expansion faster while leaving bound. Structures alone, but simple hides a headache. If you try to compute the vacuum energy from quantum fields, the sum of 0-point energies of all modes, you get an absurd answer, an energy density larger than what we observe by 60 to 120 orders of magnitude, depending on the cutoff. That mismatch is not a small tweak, it's a screaming discrepancy. Perhaps the symmetry cancels the vacuum energy exactly, and what we call dark energy is something else, a slowly rolling field quintessence, a modification of gravity at the largest scales or dynamics that screen new forces locally while letting them act cosmologically. Each of these possibilities predicts small deviations from W equals -1, or changes in how structures grow over time. That is why modern surveys care about both geometry distances and growth. How clumping precedes the pair helps break degeneracies between new energy and new gravity. There are live tensions in the data, and they're precisely the kind of tensions that make cosmology exciting rather than fragile. One is the Hubble tension, the expansion rate inferred locally from supernovae and Cepheids and other distance ladders comes out a bit higher than the value inferred from the early universe when you fit the CMB within the standard model. Another is a mild mismatch in how lumpy the present-day universe appears to be compared to CMB-based expectations, the SATE tension. These could be systematics that better calibration will smooth away. Or they could be cracks where new physics peeks through early dark energy that briefly altered the expansion before recombination. Interactions in the neutrino sector, unexpected astrophysics. The scientific posture is to sharpen the measurements and let the chips fall. If the standard model of cosmology bends, it will bend toward a truer description. Neutrinos sit at a crossroads of these stories. They were long thought massless, Now we know they oscillate between flavors which requires mass. Those masses are tiny compared to other particles, but cosmology is exquisitely sensitive to even small amounts. Neutrinos stream freely when the universe is young and hot. Their high velocities suppress the growth of structure on small scales. That leaves a signature in the matter-power spectrum and in weak lensing maps, letting cosmologists set an upper bound on the sum of neutrino masses. Particle experiments attack from the other side. Beta decay endpoint measurements try to weigh the electron-neutrino directly. Neutrinoless double beta decay experiments hunt for a rare process that would reveal neutrinos to be Majorana particles that are their own antiparticles and would violate lepton number. If neutrinos are Majorana and heavy cousins existed in the early universe, their CP-violating decays could have produced a lepton asymmetry that later converted into the baryon asymmetry. We observe a beautiful route to why there is matter called leptogenesis. Long baseline experiments are being built to measure neutrino mixing with enough precision to pin down CP violation in the neutrino sector. Cosmological surveys will in parallel squeeze the sum of masses. The payoff is not only knowledge about a ghostly particle, but a plausible link in the chain that allowed atoms to outnumber anti-atoms. How will we decide among these ideas? With an orchestra of instruments rather than a single solo. Telescope arrays map weak lensing and galaxy clustering across huge volumes to trace both geometry and growth. Spectroscopic surveys measure the baryon acoustic oscillation scale at different redshifts, anchoring the expansion history. CMB polarization maps chase primordial B modes and pin curvature, tighter feeding back on inflation's story and the calibration of late-time probes. Underground detectors push deeper into parameter space for WIMPs and coherent neutrino scattering, while low-noise radio and microwave experiments sweep for axions. Pulsar timing arrays listen for a nanohertz gravitational wave background, and in doing so constrain how black holes and galaxies assemble the very process dark matter choreographed. Laboratory clocks compare frequencies across months and years to test whether constants drift, while atom interferometers and torsion balances look for fifth forces that screamed modified gravity would hide in plain sight. It is a web. No single measurement answers every question, but the consistency of many measurements at once can rule whole classes of theories in or out. Underlying all this empiricism is a subtle lesson about explanation. It's tempting to say dark energy is weird, therefore our universe must be rare and selected. Perhaps. But selection arguments only become genuinely scientific when you can compute a distribution from a concrete theory and then condition on necessary preconditions for observers: long-lived stars, chemical richness, stable structure. If eternal inflation or a deeper quantum cosmology gives you a real prior over vacuum energies, then yes, the small positive value we measure fits the anthropic filter beautifully, much larger, and galaxies never form. If no such prior emerges, invoking selection is just a way of saying we don't know. The same intellectual discipline applies to dark matter candidates. It's easy to propose a particle whose only property is to be invisible. It's harder and better to propose one that nests into a broader theoretical framework, solving, say, a symmetry problem, and that makes predictions across domains a signal in a haloscope, a tweak in stellar cooling, a trace in structure at dwarf galaxy scales. Theories that touch many facts at once are the ones that survive. You can hear beneath the technicalities a steady drumbeat. The cosmos is legible because its largeness doesn't erase its logic. The same gravity that shapes a galaxy's rotation curve threads through the statistical pattern on the microwave sky. The same neutrinos that flit through your thumbnail by the tens of billions each second left their fingerprints in the way galaxies clump. The same quantum uncertainty that seeds inflation's ripples forbids us from pinning the vacuum energy to zero without a mechanism. In that coherence, there's a kind of reassurance. We might not yet know the names of all the actors, but we have the script structure, and each new observation helps us read the next line correctly. And when we circle back to the original question, why are we here, these details tighten the answer without extinguishing wonder. We are here because the universe allowed scaffolds of invisible matter to settle into halos early so gas could cool and stars could ignite. Because the background expansion was gentle enough for long enough for galaxies to assemble before acceleration pulled them apart. Because neutrinos were light enough not to erase structure but heavy enough to reveal physics beyond the first draft of the standard model. Because the values of a handful of numbers, vacuum energy, particle masses, coupling strengths landed in a corridor where free energy can flow for billions of years. It is not fate in the storytelling sense, it is permission granted by law and seized by chemistry and evolution. Next, we should knit one more thread through the tapestry, how these invisible components and tiny particles write themselves into the everyday facts of a living planet: climate stability, geological cycles, and the availability of energy. Gradients life can actually use. In other words, let's bring the cosmic down to the local and ask how the deep parameters of the universe whisper into the weathering of rocks, the breathing of oceans, and the tempo of evolution. That is perhaps the most intimate face of cosmology, the way the widest scales set the boundary conditions for the narrowest lives. Let's bring the vastness down to the ground under our feet and ask a very local version of the cosmic question given the laws and numbers we've been discussing. How does a planet like ours keep the lights on for biology for billions of years? The answer is a chain of feedbacks and budgets: energy budgets from the star, volatile budgets for air and water, heat budgets inside the rock, and information budgets for life itself. None of these pieces is guaranteed on a random world, but together they define a corridor wide enough for nature's inventiveness to walk through. Start with the star-planet energy exchange, because that is the master dial for climate. The sun sets a flux at the top of Earth's atmosphere. Some of that light is reflected to space by clouds, ice, and bright deserts. The rest is absorbed by air and ground and re-radiated in infrared. Greenhouse gases, water vapor, carbon dioxide, methane, and a scattering of others absorb a slice of that infrared and re-radiate in all directions, warming the surface. Those few molecules, though, scarce act like well-placed insulation, and they sit inside feedback loops. Warm air holds more water vapor. Water vapor is itself a greenhouse gas, so a small warming amplifies itself. Clouds can enhance or diminish warming depending on their type and height. Ice and snow are bright. When warming shrinks them, the surface darkens and absorbs more light, further warming in a classic positive feedback. In that maze of loops, one slow stabilizing feedback dominates the long-term, the carbonate-silicate cycle, Earth's thermostat. It works like this. Carbon dioxide dissolves in rainwater and forms a weak acid. That slightly acidic rain attacks silicate rocks on land, weathering them and carrying ions to the ocean. Marine organisms and inorganic processes turn those ions into carbonate minerals which are buried in sediments. Plate tectonics subducts those sediments. Volcanic activity and metamorphism return carbon dioxide to the air. Speed up weathering by raising temperature, by raising rainfall, by lifting mountain ranges, and you draw down atmospheric carbon dioxide faster, cooling the climate back. Slow weathering and volcanic outgassing gradually rebuilds carbon dioxide, warming the planet. It's not a quick control. It takes hundreds of thousands to millions of years to bite. But on geological timescales, it's a negative feedback that has helped keep Earth's surface temperature within modest bounds, while the sun brightened by tens of % over 4 billion years. That quiet chemical loop is one reason rivers still flow and oceans haven't boiled. Plate tectonics is the conveyor belt that keeps the thermostat supplied with broken rock and a path to recycle carbon. Without moving plates, fresh silicates are not continually uplifted to the rain. Without subduction, carbonates don't return carbon dioxide to the sky. Why does Earth have mobile plates when Mars and Venus appear to be stagnant-lid worlds with rigid outer shells? Partly its size and heat. Earth is big enough to retain internal heat from accretion and differentiation, and from the decay of radioactive uranium, thorium, and potassium elements forged long ago in stars and delivered to the forming planet. That heat drives convection in the mantle. Water probably delivered early by icy planetesimals and then recycled into the interior weakens minerals and lubricates faults. It lowers the melting point of rocks at subduction zones. It helps plates bend and dive. The result is a mobile mosaic of slabs that continually create ocean floor at ridges and drag it back down in trenches. That machinery couples the deep interior to climate. It seeds volcanoes that outgas to the atmosphere. It renews crust so that weathering can proceed. It drives the slow dance of continents that lifts mountain chains and draws down carbon dioxide. The thermostat is a geochemical symphony, and plate tectonics is the percussion section that keeps time. Magnetism adds a shield. The atmosphere you need for climate is vulnerable to the star's wind and high-energy photons. A global magnetic field deflects charged particles and helps protect the upper atmosphere from erosion. Earth's field comes from a dynamo, convective motion of electrically conducting fluid in the outer core. That motion is sustained by heat escaping from the core into the mantle, and in the last billion years or so by the growth of the solid inner core, releasing latent heat and light elements that drive buoyancy. The dynamo needs three ingredients: energy to stir rotation, to organize the flow into helical patterns, and an electrically conducting medium. Small rocky planets cool faster and may quench their dynamos early. Slow rotation weakens organization. Different thermal histories change the timing of inner core growth. Mars likely lost its dynamo early, and with it much of its atmosphere over eons. Venus may still be hot inside, but rotates extremely slowly and lacks a global field. The contrast sets a lesson in bold type. The same physics that sets climate also sets the shield that helps it endure. Water is a central character with two faces. As a greenhouse gas and a cloud maker, it participates in rapid climate feedbacks. As a rock softener and lubricant, it participates in tectonics. But too much or too little can be a problem. An ocean world with crushing depths could bury its crust under high-pressure ice at the seafloor, sealing the ocean away from volcanism and the carbon cycle. A desert world struggles to weather rocks efficiently and may fail to draw down carbon dioxide when the sun brightens. Delivery matters. Some fraction of Earth's water was likely outgassed from the interior. Some came from early impacts by water-rich bodies. The exact partition remains a lively area of research, but the message is clear: volatile inventories are not arbitrary. They are outcomes of planetary growth, impact history, and early outgassing, and they set the stage for habitability. Spin and tilt the planet's rotation rate and obliquity modulate climate as well. Earth's 23.5-degree tilt gives us seasons. Its relatively rapid spin gives us a strong Coriolis force that organizes atmospheric and oceanic circulation into familiar bands and gyres. Over tens to hundreds of thousands of years, slow cyclic variations in Earth's orbit and tilt the Milankovitch cycles shift sunlight between latitudes and seasons, pacing ice ages by nudging the climate system across thresholds. The Moon, probably born from a giant impact early on, has likely helped keep Earth's obliquity within moderate bounds by stabilizing the planet's spin axis against wild, chaotic swings. That stability is not strictly necessary for life. Nature can cope with more than we often assume, but it smooths the ride for complex ecosystems. Tides too might have mattered for life's origin by creating alternating wet and dry environments that drive polymerization chemistry, and they continue to matter by stirring oceans and mixing nutrients. A living planet does not merely sit on its geology, it participates in it. Early life exhaled methane, later life exhaled oxygen. The Great Oxidation Event, around 2.5 billion years ago, was a planetary revolution. Oxygenic photosynthesis on a global scale changed the redox state of the surface environment. Oxygen destroyed many methane greenhouse pathways, perhaps triggering snowball Earth episodes, global or near-global glaciations, that later ended as volcanoes rebuilt carbon dioxide. Oxygen also opened high-energy metabolisms and complex development, eventually feeding multicellular life, and much later large nervous systems. Life sculpts climate, and climate sculpts life. When you zoom out, the biosphere looks like a layer of computational chemistry on top of a thermodynamic planet, adjusting its own inputs and outputs through evolution. That feedback is delicate, and powerful forests modulate regional rain, phytoplankton seed clouds, soils store and release carbon. The line between geophysical and biological control blurs. Now place Earth in a gallery of worlds. Venus sits closer to the Sun, under a dense atmosphere, where carbon dioxide is not cycling into rocks but trapped aloft. Water, if abundant early, was likely lost by photodissociation and escape. The lack of a cold trap in a moist upper atmosphere accelerated loss. Without oceans, weathering could not draw down carbon dioxide. Without plate tectonics, carbon could not be recycled. The planet's present hellish climate is a stable state given its parameters. Mars sits farther out, small and cold. It almost certainly had flowing water early, but with weak gravity, a lack of a long-lived dynamo, and a rapidly cooling interior, it could neither hold a thick atmosphere nor maintain vigorous tectonics. It froze and dried. Between those two lies Earth's path, large enough to hold air and water hot enough inside to remain geologically active, placed where stellar light can be moderated by greenhouse gases into clement temperatures and gifted with a chemical cycle that buffers change. That list of just rights can sound too neat, so it's worth underlining that many are ranges, not knife edges. A world can be habitable with higher carbon dioxide if it sits farther from its star, with lower carbon dioxide if it sits closer, with slower rotation if its atmosphere is thicker, with faster rotation if its day-night heat transport is weak. Habitability is a space with multiple axes and many paths through the middle. This is good news for exoplanets. Around cool red dwarfs, the most common stars' habitable zones lie close in. Planets there are likely tidally locked, showing one face to the star, and the stars can be magnetically active, flaring often. Those facts challenge atmospheres. Can they survive? Can they move heat from day to night? Models suggest that with enough air, with oceans, and with a magnetic field, such worlds can avoid atmospheric collapse on the dark side and can shield themselves from some stellar tantrums. But the balance is tight and depends on the star's history. If the star spent hundreds of millions of years in a bright, violent youth, it might strip fledgling atmospheres before life gets started. Here again you hear the refrain: energy budgets, volatile budgets, and magnetic budgets decide. Internal heat budgets widen the story beyond surface habitability. Tidal kneading keeps the interiors of some moons warm. Europa and Enceladus likely host subsurface oceans in contact with rocky seafloors where chemical gradients could power life. Those are worlds lit from below, not above. In such niches, sunlight is irrelevant. Redox chemistry drives metabolism. Hydrothermal systems on Earth are proofs of concept ecosystems built on hydrogen, methane, and sulfides. If we find life elsewhere, it might well be in a dark ocean before we ever catch a breath of an alien forest. The physics is the same, gradients, flows, and networks, but the setting is different, and the timescales and evolutionary trajectories might be too. The faint young sun paradox is a useful cautionary tale about how these pieces interlock. Early in Earth's history, the sun was about 30% dimmer than today. By simple arithmetic, the oceans should have been frozen, yet geological evidence points to liquid water and later early life. The resolution lies in greenhouse gases, an albedo higher atmospheric carbon dioxide, and methane, perhaps traces of hydrogen from volcanic outgassing, and darker surfaces compensated for the fainter star. Over time, as the sun brightened, the thermostat cranked greenhouse gases down through faster weathering. Life's appearance altered that balanced methane-producing microbes, warming the planet oxygen-producing microbes, later cooling it in bursts. A living climate is a moving target stabilized by multiple feedbacks, some geological, some biological. If we want to turn these insights into a program for finding other heres, we need observables. We can read the atmospheres of transiting exoplanets as starlight filters through their airs, looking for features of water vapor, carbon dioxide, methane, and oxygen. We can measure thermal emission and watch as a planet rotates, reconstructing crude maps of continents and oceans from the way the light changes. Albedo variations over a day tell you something about land-sea contrasts. Glints tell you about smooth liquids. We can look for outgassing volcanic sulfur dioxide or carbon monoxide that hints at tectonics, or at least vigorous resurfacing. We can infer the presence of a magnetic field indirectly from auroral emissions or from the way a planet carves a cavity in its star's wind. And we can be disciplined about biosignatures. Oxygen alone can be produced abiotically under some conditions. Methane alone can be geological. The power lies in combinations out of equilibrium oxygen plus methane, or oxygen alongside a spectrum of reduced gases and surface pigments that modulate the reflection in telltale ways. Even then, context is everything. Star type, UV spectrum, planet mass, and geologic cycles all feed the interpretation. You can already see the chain running through this. Cosmology sets the rules for stars and their lifetimes. Stellar physics sets the light and fury a planet receives. Planetary physics sets the cycles that regulate climate. Geology sets the gradients life can use. Life once present modifies the cycles and gradients and creates new ones. Why are we here becomes why did a world land in the corridor where these loops close comfortably for a very long time? The answer is not a single fact. It's a story about sufficient conditions, long-lived stars, an atmosphere that can be retained, interior heat that drives recycling, a carbon cycle that can counter a brightening sun, a shield against stellar wind, and a volatile inventory that avoids extremes. Worlds can miss one or two and still harbour life, especially subsurface life. To support an open-ended evolutionary experiment culminating in technological minds, the corridor probably narrows. You want stability plus variability, energy plus contingency, enough time under relatively clement skies for complexity to build, stumble, and build again. There's also a sobering coda embedded in the thermostat. The negative feedback that kept Earth temperate over deep time works on slow timescales. On human timescales, the climate responds to the immediate radiative forcing. The carbonate-silicate cycle will not ride to anyone's rescue in mere centuries. That is not a digression from cosmology. It is a lesson drawn straight from the physics of feedbacks. We have learned by reading the universe how delicate and precious long-term stability is. Wisdom is at least in part the art of leaving the slow feedbacks time to work. So the cosmic and the local close a loop. Dark matter's quiet gravity sculpted the halos that gave us galaxies and the heavy elements our planet needed. The early universe's ripples set the seeds for stars like the Sunday. The small, positive, dark energy we measure granted billions of years for galaxies to assemble before the expansion thins the night. Radioactive isotopes born in ancient stars still warm Earth's interior and power, the engine of plate tectonics. A cooling core sustains a dynamo that protects an atmosphere whose composition is tuned by rock, water, air chemistry, and life to keep energy flowing at the right rate. And within that flow, chemistry found memory. Memory found selection. Selection found curiosity. When you trace it that way, because we have to be is not an empty slogan. It's a compact way of pointing at a mesh of lawful permissions that reaches from the first seconds after the hot beginning to the breath you are taking now. Where do we go from here? Outward again toward the survey of nearby planetary systems for worlds that sit in their own corridors of possibility, and inward toward laboratory studies that mimic early Earth chemistry under tides, lightning, and minerals watching polymers learn to copy. And perhaps after a long arc of science, we return to the original phrasing not as a dismissal but as an invitation. If we are here because a lawful universe allows islands of long-lived free energy and robust records, then the most honest way to honour that is to keep learning how the islands form, how they endure, and how to be good inhabitants while we have our time under the star that made us. If we want to find other heres, we have to learn how to read a planet's autobiography from starlight. That is the exquisite trick of modern astronomy. You never touch the thing you study. You let the universe write on light, and then you learn to read. When a planet passes in front of its star, some of the starlight filters through a sliver of atmosphere before it reaches us. Molecules in that air leave fingerprints absorption features at particular wavelengths. Measure the tiny change in the star's spectrum during a transit, and you can infer the gases present. Watch the planet slip behind the star, a secondary eclipse, and you momentarily subtract the star's light from star plus planet, isolating the planet's own glow. Track the small repeating, brightening and dimming over an orbit, the phase curve, and you learn how heat is moved from day to night, where the clouds are present, and how reflective the surface or atmosphere is. Each of these is a thin slice of truth. Taken together, they become a portrait. Some worlds, especially those around nearby smaller stars, can be imaged directly. You block the star's blinding light with a coronagraph, a sophisticated occulting mask and wavefront control system that digs a dark hole in the star's diffraction pattern, and you look for the faint dot of a planet next to it. The challenge is contrast. An Earth twin next to a Sun twin is roughly a 10 billion to 1 problem at visible wavelengths. That is beyond casual engineering. It is a discipline. Space telescopes win on stability. Giant ground telescopes win on raw collecting area and adaptive optics. A third idea is disarmingly simple. Fly a free-flying starshade tens of thousands of kilometers from a space telescope and cast a perfect artificial eclipse across the telescope's pupil. You lose flexibility, you gain contrast. However you do it, direct imaging lets you measure reflected light and polarization, which are sensitive to clouds, aerosols, surface glints, and even pigments. The first generation of such measurements is already teaching us how diverse cloud decks and hazes can be. The next will push towards smaller, cooler worlds. Once the photons are in hand, the hard work begins. Atmospheres are three-dimensional, dynamic and cloudy, and our data are sparse. We use statistical retrieval methods to infer compositions, and temperatures write down a physics-based forward model, encode what you know and don't, and let Bayesian algorithms explore the space of atmospheres consistent with the data. Degeneracies are everywhere. A high cloud deck can masquerade as a low abundance of an absorbing gas. Patchy clouds on the day side can mimic a temperature inversion. Metallicity mean molecular weight and scale height tangle their effect. The remedy is context. Observe in multiple bands, combine transit spectra with eclipses and phase curves, fold in what the star's ultraviolet output does to photochemistry. Ask what geochemistry plausibly outgasses, and treat the problem as the whole. The goal is not to extract more certainty than the light contains. It is to keep your inferences honest. What would count as a breath then? Evidence for life. The simplest idea is chemical disequilibrium. Left alone, atmospheres drift toward balance. Life fights that drift by tapping gradients and exhaling the products of metabolism. Oxygen alongside methane is the canonical pair on Earth. Each gas helps destroy the other, so their long-term coexistence implies a source that keeps replenishing them. There are many such pairs, and most have caveats. Oxygen can be made abiotically. if a planet loses water to space and the hydrogen escapes, leaving oxygen behind. Methane can be geological, so the rule is do not trust a single molecule. Trust patterns. Look for oxygen together with a spectrum of reduced gases that should not survive with it. Look for seasonal cycles in those gases. Look for surface colours that change the reflectance in ways consistent with pigments on Earth. There is a sharp red edge from vegetation. Look for polarization signatures that betray organised chiral molecules. None of these alone will slam the gavel. Together they can. Agnostic biosignatures push the idea further. Instead of hunting particular molecules associated with the one biology we know, ask whether the atmosphere sits improbably far from thermodynamic balance, given the planet's likely surface, temperature, stellar spectrum, and geologic fluxes. Ask whether the network of chemical reactions you would infer from the spectrum has the telltale topology of metabolism, modularity, feedback, careful reuse of intermediates, rather than the scatter of a purely geochemical soup. Ask whether the information content of the spectrum itself, when compressed and compared across time, looks like a system with memory and regulation. These are new tools. They will not hand us a headline on their own. But they make the search less parochial, and they are rooted in the same physics we trust elsewhere: gradients, flows, and constrained complexity. Technosignatures sit at the other end of the spectrum, not the chemical consequences of metabolism, but the side effects of technology. Narrowband radio lines are attractive because nature rarely produces them. A sweeping laser pulse at an unusual wavelength would stand out for similar reasons. Waste heat from large-scale energy use would glow in the mid-infrared, a muted halo of entropy. Artificial gases, chlorofluorocarbons for instance, have distinct spectral fingerprints and no plausible large abiotic sources, though they are short-lived and easiest to see, only if present in uncomfortably large amounts. Night-side illumination on a tidally locked world would have a very particular spectrum and geometry. Even peculiar transit shapes, boxy dips, asymmetries, or deepening and shallowing that follow cycles not explained by orbits could be hints of structures. The danger here is imaginative overreach. Natural astrophysics is richer than our catalogues. Dust rings, star spots, disintegrating exomoons, and instrument systematics have all played the role of mystery and then yielded to patient work. The discipline we bring to biosignatures, multiple lines of evidence, context, and a high burden of proof we must bring to technosignatures as well. Selection effects shape these searches in a way that is easy to miss. We are best at finding big signals around small stars. That biases early samples toward planets that are close to their suns, tidally locked, bathed in frequent flares, and embedded in harsher ultraviolet fields. Life may thrive there. It may not. The point is not to generalize too soon. Similarly, our sensitivity to radio or laser beacons presumes other minds want to call attention to themselves in frequencies and modulations we can detect at the times we are listening. Waste heat searches presume energy economies that light up the infrared sky. If advanced societies adopt frugal strategies that compute in the cold and keep power budgets sparse, they will be dim by design. Even reciprocity strategies looking preferentially at stars from which Earth transits the Sun on the logic that they could discover us by the same method are guesses about behavior. None of this undermines the value of looking. It simply keeps us humble about the sociology we're inferring from silence. Meanwhile, the origin of life story on Earth keeps gathering practical detail. Laboratory cycles in microenvironments, minerals that catalyze ponds, that concentrate vents, that supply gradients, are beginning to stitch together viable pathways, from simple feedstocks to replicators and compartments. Short RNA-like polymers can be coaxed to copy segments of themselves. Lipid vesicles can grow and divide, capturing catalysts. Peptides and nucleic acids can form mutualistic systems in which each helps the other assemble. Ultraviolet light and wet-dry cycling drive reactions that stall in constant conditions while surfaces template order that would be too improbable in bulk solution. None of these experiments recreates life. That is not the current aim. The aim is to demonstrate that chemistry can climb the staircase by many steps without miracles, and that each step is governed by the same thermodynamics we see in planets and stars. Take a gradient separate fast from slow pathways and select what persists. You can connect that chemistry to the oldest rocks. Carbonate globules in ancient meteorites, isotopic ratios in sediments, sulfur, redox states through time, all are trace records of a planet settling into cycles that life soon joined. Exchange between Mars and Earth by impact ejector lithopanspermia is a physical process we can quantify. Rocks launched by impacts spend thousands to millions of years in space. Some arrive intact. Microbes on Earth can survive extremes of desiccation and cold in dormancy. It is not wild then to ask whether the first seed in one world's garden was windblown from the others. Interstellar panspermia is harder by many orders of magnitude. Distances, times, and radiation hazards mount. But even on that grander scale, the discovery of interstellar visitors like Oumuamua reminded us that kilometre-scale bodies wander between stars. They are probably too rare and too hostile to be serious life ferries. They are perfect prompts to keep our imagination honest. From chemistry to evolution, the question of contingency returns. Are minds like ours rare flukes, or the likely endpoint of certain ecological games? Convergence is our best clue. Eyes evolved many times independently. So did echolocation, sociality, and tool use. Wherever there is energy to be saved by prediction, by building an internal model of the world and using it to get food, avoid being food, and find mate selection, can favor nervous systems that compress regularities into computation. Brains are expensive tissue. They are justified when the return on prediction is high. On land, hands, and fire amplified the advantages of foresight dramatically. In the sea, different constraints dominate. Whether intelligence in the technological sense is a narrow ridge or a broad plateau in evolutionary possibility space is unsettled. The safe statement is this: prediction machines make sense in many environments over long times. They will arise more than once given time and flux. Whether they coordinate to send beacons or decide to stay quiet is a separate story. This is the point where the Fermi question, where is everybody, turns from equipped to a framework. There are filters in the chain, from star formation to galaxies to rocky worlds to replicators to civilizations to long-lived energy-literate cultures. Some filters are astrophysical supernova rates, gamma-ray bursts, metallicity thresholds for planet formation. Some are planetary volatile delivery tectonics, magnetic shielding. Some are biochemical, the difficulty of robust replication and metabolism. Some are cultural learning to manage growth, energy, and risk without destroying the substrate of civilization. Our observation, no clear sky-wide technosignatures so far, could be telling us that one or more of these filters is steep. It could also be telling us that we are early, or that our strategies probe the wrong phase space. The honest response is to keep placing constraints, compare them to models of the galaxy's history, and resist the urge to make sociology do too much work in a data-poor regime. Amid all this, an astronomy of responsibility takes shape. If we discover a biosignature, we will need protocols to avoid self-deception, independent confirmation with different instruments and methods, careful checks for confounders, a ladder of confidence that makes each claim explicit. If we send probes to potentially living worlds, we must prevent forward contamination. If we return samples, we must prevent back contamination. If we broadcast deliberately, we should discuss widely and openly what we are doing and why. None of this is an add-on to the science. It is part of being a good participant in a universe that allows knowers. The same laws that give us the stars give us consequences, and all the time the tools sharpen. Telescopes that can resolve the atmospheres of temperate rocky worlds orbiting nearby stars move from sketches to hardware. Giant mirrors on the ground learn to hold a star's image, still to micro-arcsecond tolerances. Spectrographs peel faint signals out of noise with cross-correlation techniques that match entire molecular templates at once. Arrays of radio dishes scan the sky with ever wider bandwidths, while time-domain observatories catch flares, eclipses, and transients that used to slip between the slats of our attention. On the biological side, microfluidic platforms let chemists run thousands of prebiotic experiments in parallel under different geologies and skies. The gap between we imagine and we can test narrows a little each year. If you zoom out and look at the through line, the answer to why are we here acquires texture without losing its spare elegance. We are here because a lawful universe produced long-lived gradients and allowed robust records to be written and preserved. Those records, first in the patterns of the early sky, then in the chemistry of a young planet, then in the genomes and cultures of living things, made memory possible. Memory allowed selection to build function, and function allowed curiosity. Everything else is embroidery. The embroidery matters. It is the difference between a barren rock and a thinking world. But the canvas is the laws, and they are generous in exactly the ways that permit meaning to take root. Where does that leave us for the next step? We have walked from the largest scales to the breath in your lungs and back again. The natural continuation is to splice time into the answer. We should look squarely at the time of arrival problem, why we find ourselves now, rather than earlier or later, and at the cultural filters that turn a habitable span into a history worth having. Cosmic hazards, sustainable energy, interstellar distances, and the mundane triumph of good governance over long horizons. These are not epilogues to a cosmology talk, they are the last mile of the same causal chain. If the universe has granted us the permissions, the question becomes, what do we do with them? If we're going to be honest about why we are here, we also have to be honest about why now. That sounds philosophical, but it's a scientific question with numbers behind it. Stars are born, shine and die. Planets condense, cool, and either keep or lose their air. Galaxies feed and quieten. There is a timetable to the cosmos, and observers, creatures who learn the timetable, can only appear during certain windows. The time of arrival question asks where, in that grand schedule, we're most likely to find ourselves. Begin with the history of star formation. The universe was more exuberant in its youth. A few billion years after the hot beginning, galaxies were churning out new stars at a rate far higher than today. Astronomers sometimes call that era cosmic noon. Since then, the star birth rate has declined as gas has been used up, heated, or blown out of galaxies. But decline does not mean silence. New suns still light every year across the sky. The mix has shifted. The long-lived red dwarfs, cooler and dimmer than our sun, dominate the census. And here a curious fact intrudes: red dwarfs can burn steadily for trillions of years, far longer than the current age of the universe. If you ask coldly at what cosmic time will most habitable hours exist, you might answer in the distant future, around small red stars, not now around yellow ones. That is one reason some cosmologists argue that the peak era for life, if all else were equal, may lie ahead, not behind. But all else is not equal. Red dwarfs are small furnaces with tempestuous childhoods. Many flare violently when young, bathing nearby planets in ultraviolet and X-ray bursts and battering atmospheres with stellar winds. Close-in orbits needed for temperate conditions around such faint stars bring tidal locking, one face in perpetual day, the other in perpetual night. Those are not automatic disqualifications. Thick atmospheres and oceans can move heat. Magnetic fields can shield. Life is inventive, but they are constraints. Add metallicity, the abundance of heavy elements that rocky planets require. The early universe had few. Generations of stars had to live and die to stock the shelves with carbon, oxygen, silicon, iron. Planet formation therefore becomes easier as the universe ages up to a point. There is a trade. Early times lack materials. Very late times may offer long starlight, but fewer new chances as gas dwindles. We live in the middle, in an era when heavy elements are plentiful, temperate worlds are common, and there is still a cosmological ocean of time for evolution to run. Why now might simply be because the shelves are well stocked and the shop is still open. There's a galactic geography to the timetable too. Not every neighborhood is equally calm. Regions near the centers of galaxies packed with stars and dust host more supernovae, and in some epochs, more gamma ray bursts, brief intense flashes that could bleach atmospheres or damage biospheres if they occurred very nearby. Far out in the sparse suburbs, heavy elements can be scarce. Between those extremes sits a broad, habitable band in the galactic disk where metallicity, radiation environment, and gravitational stability are, on average, kinder. Our sun orbits there, neither too close to the crowded center nor too far into the metal-poor outskirts. Even within that band, hazards arrive on their own schedules. Close passages of other stars can jiggle the distant Oort cloud and send comets sunward. Spiral arms concentrate gas and star formation and may raise the background of supernovae as we drift through them on 100-million-year scales. None of this makes Earth special in a grandiose sense. It makes it typical of a certain corridor, a time and place where catastrophes are infrequent enough, resources abundant enough, and gradients stable enough for biology to write long chapters. Then we confront the filters. Between a stellar nursery and a technological culture sit many gates, any one of which may be narrow. The origin of robust replication, the jump to cells, the leap to oxygenic photosynthesis, the endosymbiotic union that built complex cells, multicellularity, nervous systems, language, culture that preserves knowledge across generations, and finally the ability to harness energy without burning the future that supplies it. The quiet sky could be telling us that one or several of those gates is steep. It could also be telling us that civilizations rarely remain loud. Perhaps most learn quickly or slowly to prefer frugality over spectacle, to compute in the cold, to keep waste heat low, to speak in local bands and narrow beams rather than sky-filling shouts. The absence of obvious signatures is not a verdict. It is a boundary condition on our expectations. Cosmic hazards are the bluntest filters. and they are worth meeting without melodrama. Asteroid and comet impacts happen. We live amid a debris field left over from planet formation, stabilized by Jupiter's gravity but not pacified. Large impacts are rare on human timescales, inevitable on geological ones. The physics of prevention is not mysterious. If you can see a threatening object early, you can nudge it. A kinetic impactor alters its orbit by a tiny amount. Gravity tractors tug gently over time. Even paint in principle changes the way sunlight pushes a body. The key is lead time. That is why methodical sky surveys matter. It is not glamorous to make a catalogue and keep it up to date. It is civilization's version of learning where the furniture is in a darkened room, so you stop stubbing your toe. Nearby supernovae and gamma ray bursts are scarcer but more powerful. A supernova within a few tens of light years could damage the ozone layer and raise ground-level ultraviolet for years. Gamma ray bursts point their beams and would need unlucky geometry to hurt us, and they appear to be less common in metal-rich galaxies like the Milky Way at present. Again, the right response is knowledge monitor massive stars nearing the ends of their lives, model atmospheric responses, build resilience in food systems. Magnetic storms from our own sun can also threaten coronal mass ejections, can induce currents in long conductors and grids. Space weather forecasting and hardened infrastructure are not indulgences. They are for a technological species a kind of planetary hygiene. None of these risks is a cosmic jury with unknowable whims. They are lawful phenomena with rates that can be estimated and mitigations that can be practiced. The quieter filters are cultural and thermodynamic. A civilization is a heat engine. It takes concentrated energy and turns it into work and waste heat. On a planetary surface, there are strict limits on how much power you can dissipate without altering climate simply by your own warmth, regardless of greenhouse gases. The number is surprisingly modest compared to the total sunlight Earth receives. Even before we imagine capturing a significant slice of starlight with vast collectors, there is a ceiling imposed by the fact that every computation, every factory, every city glows in the infrared. This is not an argument against growth. It is a reminder that growth must eventually decouple from raw energy throughput or move where radiators can run colder off-world, further from the sun, into environments where waste heat can be rejected without cooking your biosphere. Kardashev's neat ladder, planetary, stellar, galactic, remains a useful metaphor, but thermodynamics suggests that the rungs are wider and stranger than simple percentages of starlight, and that wisdom may lie in moving outward and slowing down. Computation, rather than in building shells that blaze. That leads to the engineering reality of travel between stars. Distances are not just large, they are regimes where familiar intuitions fail. Chemical rockets, even the best, will take tens of thousands of years to reach the nearest star. Beamed light sails, ultra-thin mirrors pushed by powerful lasers could, in principle, deliver gram-scale probes to nearby systems in decades, carrying cameras and sensors and chirping home brief data bursts. Fusion rockets could, in theory, raise payload mass and shorten trip time, but they require control over reactions and fuel cycles we do not yet have. Antimatter carries stupendous energy per unit mass, but is fantastically hard to make and store. The Bussard ramjet, a scoop that gathers interstellar hydrogen to fuse as it flies, runs into practical obstacles, drag fuel density, fusion cross-sections. None of these ideas is magic, none is close to easy. The likely first wave will be small and robotic, a series of scouts and pebbles. Later waves, if they come, will look more like slow, redundant arcs than like knife-point dashes, ecosystems exported in miniature, designed for maintenance and repair, or even embryo ships that grow their crews at destination under watchful machines. The thread tying them together is patience, not bravado. There is another way to cross cosmic distances without moving engines. You can move information. A species that takes itself seriously as a steward of knowledge will care about how to encode, correct, and propagate that knowledge across generations that may be interrupted by accidents. The universe is kind to error-correcting codes. It is built on them at deep levels. Holography suggests that geometry itself might be an error-correcting encoding of quantum information. Biology discovered redundancy and proofreading early and never let them go. Our archives should do the same. That sounds prosaic next to starships, but continuity of memory is the one technology every long-lived civilization will share. If we ever find a message from far away, I suspect it will not be a song, but a library compressed, self-describing and patient. All of this loops back to the great filter idea in a way that is less gloomy than it first appears. Filters can be gates to wisdom as well as traps. A species that learns planetary defense, space, weather, hygiene, and energy accounting is a species learning to read its thermodynamic budget. A species that builds institutions that outlast tempers and election cycles is, in a very literal sense, a species that has decided to be an error-correcting code for itself. The cosmos supplies long spans of time and lawful regularities. Whether we pass through the filters is not fate, it is practice. There is also the arithmetic of typicality. Some argue that if civilizations often self-destruct early, the fact that we find ourselves before a putative, much larger future of red dwarf hosted life is unsurprising. We are sampling from a distribution whose tail is thin. Others point out that there may be more than one typicality at work, typical among all observer moments, or among first technical species in a given galaxy, or among those who develop radios. The lesson for my taste is modesty. Use typicality when it helps calibrate expectations, but do not load it with moral weight. The right thing to do does not depend on whether our arrival is early or late. It depends on what kind of ancestors we decide to be. If we step back and try to see the whole, the picture is coherent. The universe began with low gravitational entropy and gentle quantum ripples. Gravity amplified the ripples into webs of dark matter and light. Stars forged heavy elements. Their death salted the disks around newborn suns. Planets assembled, some cooled under blankets of air and water. Chemistry climbed a staircase toward memory and metabolism. Selection built function. Minds learned to compress regularities into mathematics and to predict. Along the way, horizons stored information, black holes taught us about entropy, and the large-scale expansion turned out to be accelerating, giving us billions of calm years for galaxies to assemble before the night thins. Now, on one world, a species wonders what to do with permission. What do? We keep the chain unbroken. We learn the sky as an early warning system, not as an omen. We match our energy use to what our planet can radiate, or we move the hottest tasks to colder places. We invest in error correction, in archives, in education, in governance that makes and keeps promises over centuries. We look outward with instruments that can read atmospheres and inward with experiments that coax lifelike networks from simple chemistry. We cultivate patience as a technology, and we make peace with the idea that meaning is local and authored, that the universe does not assign it but allows it, and that our job is to write well within the laws. If you've stayed with the argument since that quick answer, because we have to be, you can now hear what it meant. It wasn't fatalism. It was a shorthand for a cascade of because statements that are one by one being turned into measurements. Because quantum fluctuations were stretched by an early accelerated phase, we see a nearly scale invariant pattern in the oldest light. Because the initial state had low gravitational entropy, there is an arrow of time and a long downhill for structure. Because dark matter formed an invisible scaffold, galaxies grew early enough. Because dark energy is small and positive, galaxies had time to assemble before the expansion pulled them apart. Because radioactive isotopes warm, Earth's mantle plates move and the carbon cycle stabilizes climate. Because chemistry can build error-correcting networks under flows of free energy, life can persist and evolve. Because cognition compresses patterns technology can plan. Each because is not a miracle, it is a permission. Taken together, they explain not why the universe chose us, but why a universe like this permits creatures like us to choose. Where should we walk next? Perhaps to the most intimate layer of all meaning as practice. We've answered the cosmological why with preconditions and measures. We've followed the thread into geology, biology, and technology. We've sketched the filters and the futures. The last step is to ask how a scientific understanding of our place can coexist with and even nourish the values that make a civilization worth sustaining, care for the fragile curiosity without vanity, and a willingness to place stones in a bridge we will never finish crossing. That too is part of why we are here. Not as a decree from the stars, but as a choice we make under them. If meaning is something we author under the laws rather than something the laws decree, then the next honest question is what practices help authors write well. Science usually enters here as a list of facts, but the deeper gift is a set of habits, ways of thinking that keep our stories tethered to the world. They are simple to name and hard to sustain: curiosity without credulity, skepticism without cynicism, love of precision without losing sight of proportion, and a willingness to update when reality says no. Those habits scale. An individual uses them to learn, an institution uses them to endure, a civilization uses them to steer. Start with the smallest unit: acclaim. A good claim carries its own uncertainty with it. You don't just say the expansion rate is this, you say the expansion rate is this plus or minus, that under these assumptions, that little plus or minus is not a hedge, it is a coordinate system for doubt. It lets other minds ask sensible questions. What would move the central value? What dominates the error? Which assumptions are load-bearing? The habit generalizes. A weather forecast is not rain or no rain. It's a probability distribution that shifts as new data arrive. A medical trial is not this drug works. It's an effect size with confidence intervals and a plan for replication. Bayes' rule, the mathematics of updating beliefs in proportion to evidence, is not some esoteric right. It is a formal expression of common sense once you have learned to think in distributions instead of certainties. The early universe taught us this by example. The pattern in the oldest light is not an allegory. It is a set of numbers with error bars that have narrowed as measurements have improved, bringing our models along with them. The same ethic of error correction shapes how we build collective memory. Nature keeps records in layers of ice, in tree rings, in sediments, in the photons of the microwave background. We keep records in archives and code repositories, in version datasets and public logs. When those records are open, redundant and interoperable truth becomes a property of the network rather than a boast from a node. Think of global navigation satellite systems and the time services that underpin them. A web of atomic clocks cross-checked and disciplined gives everyone the same seconds. Think of climate reanalyses. Scattered observations, balloons, satellites, buoys are pulled into a coherent picture by state estimation, the same Kalman filter logic that guides aircraft and smooths noise in sensors. The mathematics of filtering and redundancy is the same whether the system is a satellite's orbit or a civilization's memory. The principle is simple: do not trust a single channel, fuse many, record provenance at every step so that you can rewind and inspect. A richer picture of responsibility emerges when you look at feedbacks. We already met planetary feedbacks, ice clouds, carbonates, and the warning that slow stabilizing loops cannot save you from fast pushes. Human systems are similar. We value efficiency for good reasons, but pure efficiency often strips out redundancy, leaving a network brittle under rare shocks. Physics teaches the difference between average and variance the hard way. Catastrophes live in tails. Heavy-tailed distributions, those with relatively high probabilities of very large events, resist naive intuitions. In power grids, in supply chains, in public health, the right posture is not to pretend tails can be trimmed to nothing, but to design so that local failures decouple rather than cascade. Electrical engineers call it islanding. Ecologists call it compartmentalization. Epidemiologists call it ring vaccination. Information theorists call it coding with interleaving. The vocabulary differs. The logic is the same structure. The couplings add, buffers keep slack where slack keeps the system in the linear regime. Energy is the other unavoidable discipline, and here physics speaks in especially plain language. You can move energy around, you can convert it cleverly, you can harvest it from gradients you used to ignore, but you cannot enjoy work without waste heat, and you cannot keep a thermal budget invisible forever. That does not condemn ambition, it shapes it. If you want heavy industry and dense cities without cooking your air, you push your energy conversions toward higher exergy and lower losses. You match demand to intermittent supply with storage and flexible loads. You do high heat tasks where heat is easy to reject. Desalination data centers, smelters, some of these belong where the radiators can run cold. The argument is not moralistic, it is thermodynamic. On a finite biosphere, comfort and computation share a radiative ceiling. Off-world, the ceiling lifts as the background temperature falls. A species that learns to externalize the hottest work while preserving the quiet cycles of its home has read the second law, not as doom but as design brief. You can read the same brief in cities. Urban heat islands are a radiative and convective problem before they are a cultural one. Surfaces with higher albedo reflect more sunlight. Trees pump latent heat into the air via transpiration. Street canyons either trap or ventilate depending on aspect ratios and prevailing winds. Particulate pollution is a boundary layer physics problem that becomes an equity problem because air does not respect property lines. There is dignity in solving these with honest physics measure, model, test, iterate. You don't need slogans when you can point to surface, energy budgets and concentration gradients and say this is why that intervention helps and this is why that one doesn't. The atmosphere is not ideological. It responds to fluxes. Ecosystems are information processors, and that is not a metaphor. Food webs route energy and matter the way circuits route signals with feedbacks and delays and gain. Robustness comes from diversity and redundancy, multiple species filling similar functional niches so that the loss of one pathway does not crash the whole computation. Tipping points are dynamical bifurcations cross a threshold in a key parameter, and the system tips into a new stable state that is hard to reverse. The literature even has early warning indicators rooted in dynamical systems theory: critical slowing down, rising variance, flickering. Those are not just picturesque phrases, they are testable signals in lake chemistry, in rangeland vegetation, in ice sheet flow. A civilization that trains itself to watch for such signals in the systems it cares about, watersheds, forests, fisheries, will not avoid every surprise, but it will learn to tell surprise from neglect. Education, in that light, is not a contest of facts, but a transmission of habits. We can teach proportional reasoning, the difference between linear and exponential growth, the way we teach multiplication tables so that infectious disease curves and compound interest stop feeling like magic. We can teach order of magnitude estimates, Fermi problems, so that any citizen can sanity check a headline claim by a quick back-of-the-envelope calculation. We can teach the grammar of uncertainty so that a forecast is not heard as we don't know, but as here is the range and here is how it narrows when new data arrive. We can keep wonder alive by showing that understanding does not erase beauty, it sharpens it. A rainbow is not less lovely because you know about dispersion. It is more so because your mind now sees the continuum from raindrop to spectrum to eye. Communication is the fragile link between understanding and action. The temptation to perform certainty is strong, especially in noisy public spaces, but confidence without calibration corrodes trust. The better virtue is legibility: say what you know, what you don't, what would change your mind, and what you will measure next. Scientists are sometimes accused of hedging. We should own the accusation and turn it into a norm. Explicit conditioning on assumptions, explicit ranges, explicit plans to update. The complementary vice is sensationalism. A single dramatic possibility stripped of its low probability travels farther than a quiet, faithful summary of a distribution. The antidote is craft narratives that carry the right structure of uncertainty without losing pace. Metaphors that illuminate without distorting. Visuals that show confidence bands as first-class citizens, not footnotes. Institutions matter because knowledge has a half-life if you do not tend it. Peer review is often criticized, often deservedly. It is a minimum, not a sacrament. Replication is better. Do it again with new data, with pre-registered analysis plans when possible, and publish the nulls. Incentives follow metrics, choose them carefully. If you reward novelty above reliability, you will get novelty and lose reliability. If you reward open data and reuse, you will get cooperative ecosystems where methods compound. The most powerful technologies for the next century, learning systems that infer patterns from large datasets, gene editing, planetary scale sensing, amplify both our capacities and our errors. Guardrails are not anti-science. They are the way a curious species keeps its tools aligned with its values. It is also worth naming the simple cultural superstition that physics can dispel the idea that scale confers meaning. The universe is vast, yes, but the equations we use are mercifully scale-free. A star-forming cloud and a swirling cup of coffee share the same dimensionless numbers if you choose the right ones. A neuron and a radio antenna obey the same electromagnetic laws. A seedling obeys the same thermodynamic constraints as a city. That symmetry is not an argument that everything is the same. It is a reminder that bigness is not a measure of worth. A planet's narrow biosphere sits a few kilometers up and down from the surface. Most of the universe is empty space. Meaning has always been made in thin films, in skin, in soil, in coastal shelves, in classrooms. Physics frees us from the anxiety that we need cosmic scale to justify local care. When you stack these habits and structures, error bars, open records, redundant networks, thermodynamic budgets, early warning indicators, education that teaches uncertainty, communication that respects attention, institutions that reward, reliability, you recognize a pattern we have met before. It is an error-correcting code. The genome is one. Black hole holography appears to be one. A good society should behave like one. Noise will always be with us. Random accidents, rare disasters, motivated errors. Codes survive noise by distributing information, checking it locally, and repairing it promptly. That is not a metaphor when it comes to governance. Distributed accountability, independent auditing, and reversible decisions are our equivalents of parity checks and syndromes. If we build them, knowledge accumulates. If we neglect them, noise wins. There is a gentler daily practice hidden in all this. Curiosity and care are often treated as different virtues. In reality, they are the same habit pointed in two directions. To be curious is to say the world is worthy of attention. To care is to say the world is worthy of protection. The muscle that lifts both is the one that refuses to treat anything as merely background. When a telescope stares at a patch of sky and integrates for hours, it is an instrument of attention. It gathers faint photons until a galaxy appears. When a field biologist kneels and counts the first spring insects, they are doing the same thing. Those practices scale to civics counting matters, especially when nothing dramatic is happening, because you only learn the baseline by tending it. What about meaning in the personal sense, the kind that people rightly refuse to outsource to physics? The modest suggestion is that scientific seeing can nourish it rather than threaten it. If you know that the iron in your blood was built in stars, that the planet's climate is a set of loops, you can draw that your own sleep and mood track the light your eyes take in, that the noise on a microphone follows a spectrum. You can name then, belonging is not a mystic fog. It is a daily recognition that you are part of lawful flows. Wonder in that register is not confusion. It is comprehension that does not run out simply because your current derivation does. There is always a next layer, a next why, a next place where the data will discipline you and then reward you with a cleaner picture. If we thread that back to our opening question, why are we here? The answer requires a quietly practical edge. We are here because a lawful cosmos made islands of long-lived free energy and allowed records to endure. We remain here and become worthy of the gift. If we behave like the systems we admire, we keep good books, we compress regularities into tools, we check one another, we plan in horizons longer than any single life, and we leave room for slack so that our networks can flex instead of shatter. None of this is news to the laws. It is us catching up with what they have always implied. What should we talk about next? Perhaps the two remaining frontiers that will press hardest on these habits in our time. Learning machines that discover patterns we do not yet understand, and planetary scale interventions deliberate, accidental, that alter the flows we depend on. Both are invitations to do our best thinking about control, transparency, and humility. Both will go better if we remember that the universe is kind to those who measure well-reasoned in distributions and choose designs that fail gracefully. In a cosmos that never promised us permanence, that I think is the closest thing we have to a recipe for staying. Step outside for a moment in your mind onto a quiet piece of ground that remembers your weight. Feel the air, ordinary nitrogen and oxygen relics of volcanoes and life braided together, moving over your skin in slow, invisible rivers. Somewhere above clouds are negotiating with sunlight over who will return more brightness to space. Somewhere beneath minerals are bargaining with carbonic rain over how much carbon to hide away. None of this asks your permission, and yet all of it sustains you. You are standing in the middle of lawful conversations that began before there were ears to hear them. Look up. The starlight that reaches you tonight set out long before the languages, long before the continents took their current shapes. It carries two kinds of memory. One is atomic, the fingerprints of elements forged in ancient furnaces and released by old catastrophes. The other is geometric, the way gravity has bent and redshifted the journey, the way expansion has stretched the night until it hums at a temperature barely above nothing. You don't have to solve an equation to feel the companionship of that light. It tells you without rhetoric that you belong to a story that is grand, precisely because it needs no author to be beautiful. If there is comfort in any of this, it is the kind that comes when confusion gives way to clarity without erasing wonder. The cosmos is not a riddle posed to trap you. It is a set of permissions. It allowed gradients to flow and matter to try forms. It allowed memory to accumulate in genomes and books and instruments. It allowed curiosity to become a way of living. The more closely you look, the kinder the pattern is. Horizons are not walls. They are ledgers that keep the second law honest. Black holes are not erasers. They are scramblers that with patience return the stories they swallow. The early universe was not a magical exception. It was a clean boundary condition that left us a sky of numbers, simple, testable, humane, in their refusal to flatter our intuitions. And here you are, a brief arrangement of atoms walking around with models of the world inside a warm skull. That is not small. To predict is to care. To measure is to respect. To admit uncertainty out loud is to give other minds a handhold on your thoughts so that it can be checked, corrected, improved, and carried forward. A species that learns those habits is a species that lengthens its own future. We talk about error-correcting codes in physics. You can be one in practice. A promise kept is a parity check on a relationship. A dataset shared is redundancy against forgetting. A plan that leaves slack for surprise is a design that stays in the linear regime when life pushes back. There is a gentleness available in this view that has nothing to do with retreat. It's the gentleness of proportion. You don't need cosmic scale to make meaning. Most of the universe is empty, and yet life has always happened in thin films on coastlines, in soils on the surfaces of leaves at the membranes of cells. The thinness is not a defect. It is where gradients concentrate and where records can be written and read. To water a sapling, to tune an instrument, to calibrate a sensor, to teach someone how to think in distributions, these are cosmic acts at the right scale, because they keep the flows going and the memory intact. If you feel a tug of humility alongside a warmth of belonging, that is exactly right. The laws did not pick you out, they allowed you. The universe will carry on when the last story you love has ended. But that does not make your care optional, it makes it precious. There are filters in front of us, thermodynamic, ecological, social, that no grand theory will navigate on our behalf. We pass them if we pass them by practicing attention together. We keep catalogues of wandering stones in the dark, not out of fear, but out of respect. We design our cities with albedo and shade and airflow in mind, because the atmosphere answers only to fluxes, not to slogans. We use energy as if waste heat matters because it does. We place the hottest computations in colder places and leave the quiet cycles of home to do what they do best. And we keep looking outward, not to flee the earth, but to finish learning the sky. Every atmosphere we read across the light years, every strange cloud deck, every surprising molecule, every hint of disequilibrium will be another mirror held up to this one world, another way to see what is robust and what is fragile. The conditions that cradle us. Perhaps we will see a signature one day that asks us to invent new words. Perhaps we will see only the patience of rocks and the poetry of weather on 1,000 silent spheres. Either way, the act of looking is part of being here honestly. It reminds us that our corner is not the center, and that our choices matter all the more because nothing outside is obliged to rescue us. If you listen carefully now, there is another sound beneath the breeze, the slow tick of planetary clocks, plate motions, magnetic reversals, the glacial breath of ice sheets. They move too slowly for any single life to notice without instruments, and that is why we build instruments and archives to guard what they learn, and schools to keep the grammar of uncertainty alive. We make ourselves larger in time by taking good notes for strangers. We inherit the world from people we will never meet and owe it in turn to those who will never know our names. That is not sentiment. It is the definition of a civilization. So take a breath. The oxygen in your lungs was made in stars. The carbon in your muscles was pulled from air by leaves or drifted down through oceans before it found you. The heat in your chest is ancient sunlight reissued. The thoughts moving through you are the latest draft of a model that began when nervous systems first learned to predict a wave's arrival. The future is not guaranteed. It is granted as a conditional renewable lease payable in attention and care. But the lease is long by any human measure, and the place is fair and the rules are clear. If you want a benediction from the laws, take this one: keep good company with truth. Measure generously, doubt cleanly, share your error bars, choose designs that fail softly. Tell the young what constellations are and where to find the pole. Teach them the difference between a claim and a distribution, between a headline and a series, between spectacle and signal. Tell them that a rainbow is dispersion and that this does not make it less beautiful. Tell them that the night is expanding and that this does not make it less intimate. Tell them that we are here not by decree but by permission, and that permission grows when we use it well. And when you are done speaking, let the quiet do some work. The planet will keep turning. The deep ocean will go on hoarding cold. Somewhere a detector will tick as a particle that almost never speaks says hello. Somewhere a leaf will unroll a sugar from light. Somewhere a child will ask why the moon doesn't fall, and someone will draw an ellipse on a napkin and make a memory. That is enough to rest on. Under a sky that is older than stories and kinder than fate, we can be small without being lost, brief without being trivial, curious without being cruel. We can be, for a while, good ancestors. And if there is an answer to why are we here worth keeping close, perhaps it is simply this: to notice, to learn, and to leave behind a world where noticing and learning remain possible, so that others standing where you are now can look up and feel at home.